Good morning. Hey, Marco. Hey, Scott.
Hey, Rich.
Let's see. Do we have Harsha here? I don't see Harsha yet. So question, is this the right link for me to have used to come in? This is the one that Mayor sent around. I tried looking for a private one where maybe each of us would get our own link, but there's actually so many KDD emails, I wasn't able to find it. There must be 100 of them. So is this an appropriate link to be on to give the presentation?
I think this is the right one.
The same one I used, so it seems to work.
Great. And then there seems to be a very large number of people here, but I assume the tutorial doesn't start for a half an hour, so.
Maybe they're early.
Could be. Cool. Welcome to everybody. I guess some of the people here in the meeting are organizers of the event, either people who help make sure that the presentations go well or otherwise. Could any of you self-identify?
Yes, I just joined. I'm Amir. I'm the student volunteer assigned to this talk, to this tutorial.
Oh, great, great. Nice to meet you, Amir.
Yes. So we still have like half an hour, right?
Right.
I think you have to make me a co-host. I think
so. And I don't. Let's see. So Mares isn't here yet either, I don't think. She might be the only one who can make you a co-host, but tell us how to do it, and I'm happy to give it a try.
I think only the host can make somebody else the co-host. So
right, and Mares may have made all of us co-hosts, so I don't know if as co-hosts the power transfers to us or not. Let's see.
I'm not a co-host because I can't share my screen.
Okay, so then maybe none of us are co-hosts.
Could be the link that we followed.
I'm going to try to share my screen just to see if that works. Okay.
Yeah.
No, host disabled, participant screen sharing. Okay, so all right, I'm going to send an email to Mares and
sure. I was also preparing like a feedback form on Google Forms. Do you think that's a good idea? Like for the tutorial, that would be good feedback for you as well as for the organizers of KDD.
So hold on, let me send an email to Mayor since that's important.
Sure.
Do you happen to know if there's a place to put passwords? I know that the email with the link came with a passcode, but Zoom never asked for it when I followed the link.
Yeah, so there's like a Zoom link with the password, so we can share that. That's perfectly okay. You shouldn't have to enter the password.
I see.
Hey, Marco, Scott, you might enjoy knowing that we had a working group meeting also scheduled for 9 a.m. Pacific time. And it was actually going to be important that you, both of you and I attend that meeting. So they're quickly rescheduling that meeting because we won't be there. So, and I was the one person who had all the information, but I failed to make the appropriate neural connection that we were actually important for the plan. So yeah, I didn't realize it.
I assume I'm never important.
Say it again.
I just assume I'm never important.
Sometimes you are important, Marco. It's rare, but you know, occasionally, yeah. So anyway, hey, so it's great to see we've already got a number of attendees, even though we haven't started yet. So that's kind of cool. I did send email to Mares. Hopefully she'll join us quickly. Is there anyone else in the call who has organizer power and can you know. Amia, I was hoping maybe you would, you know, as the representative from KDD that they would have given you. You're muted, just so you know, Amia.
Yeah. I think it's just one volunteer for each
Gotcha.
hands-on tutorial. Yeah.
Gotcha.
But if anything urgent happens, I can always contact them and they'll just
Right.
jump in.
Right.
Yeah.
Well, hopefully Mares will join us quickly. So.
Yes.
Let's see. Are there other links that any of the presenters, Marco or Scott, know that we should be using instead? Because maybe those other links would automatically grant us the power. I'm going to search through my KDD email.
I think that's how Zoom works. I think someone is the host and that's that. They have to be logged in and they're the host. Like it's not a specific link that you join to.
Right. I mean, I do have a username and password, but I think that's just for the entire KDD event.
Do you want me to ask the organizers to maybe just ping?
If you think they're not like busy putting out a dozen other fires and could help us, sure, that'd be great.
Okay, let me do that.
Just in case we don't get Mares, you know.
I think I just managed to log in with her account. So
Oh,
how do
there
I
you go.
add people as hosts?
Scott got it.
So you logged in with whose account?
I just
The
traced through
Zoom.
the emails from MERS. I'm now logged as KDD Zoom 11, so I think I'm the host now.
Yeah, you
Okay,
are.
great. Does
It
that
showed
mean
up.
that you can make us now co-hosts or give us authority
theory.
to share a screen?
Yeah, I think you click on someone and the three dots, right?
Yep.
So first
I'm
of all,
making Rich a co-host.
I see I'm now a
Marco,
co-host.
co-host.
So I'm going to try sharing a screen suddenly and see if that works. And it looks like I now have the ability to share a screen. So,
Yeah, we can see your screen.
great job, Scott. I will stop
Okay.
sharing a screen. How do I do that? Cool. Stop share. All right, great. Fantastic. Very good. Good job, Scott.
So let me try
Amia, I don't know if
sharing
you heard
myself.
that, but Scott managed to log in, I guess, with Mare's credentials. And now he's able to make us co-hosts. So can you also make Amia a co-host, Scott?
Can you try and do that just in case I need to log out? Because I might be blocking MERS' ability to log in by doing this.
I see. Okay,
I just want to make sure if I log out and log back in, you could make me a co-host as well.
All right, Mia, I will try to make you a co-host.
Okay, thank you.
Yeah, no, I don't see. To do it, Scott, you clicked on more when you saw Mia's.
I clicked on the three dots on his thing and there's like mute audio, stop video, blah, 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 make host, make co-host.
Yeah, and I don't see a make host, make co-host when I do it.
Let me try and make you a host. You don't see it either, Marco, I guess.
No.
Okay, I'm gonna make Rich the host.
Aha, I just became the host. And now I am able to make Amia a co-host.
Great.
Do you want to make Amia's iPad co-host of the meeting? I'm going to say yes. Cool. So Amia, you are now co-host.
Okay, I'm going to log out then.
Okay,
just so
great.
that I want MERS to have some
Scott.
issues logging in.
Great.
So let me try sharing my screen. With
Yeah, this is a good time.
To see. One sec.
I don't see it yet, but.
Yeah, I haven't shared yet.
Okay.
I'm just closing other stuff that may pop up. I don't want to pop up during the presentation, like Teams. And Outlook and stuff like that. Let's see if this works.
I now see your screen, so it's working.
Do you also see?
The resolution is
in
pretty
full
poor,
screen?
but maybe that's just a question of time.
Is it okay now?
Yeah, look, the resolution is still, marginal, but I think that might be a video bandwidth issue. They may intentionally be lowering resolution with so many Zoom users at the meeting. Oh, now it's getting sharper. It's almost like a
your internet,
JPEG.
Marco.
It's almost
What?
like a JPEG that came in lower resolution and now it's getting better.
Can you tell me if you guys can hear my audio? Like I'm gonna play the video and you tell me. Okay.
Sure, go ahead. I don't hear anything yet. Still don't
My
hear
guess is
anything.
under the microphone on the bottom left, you might have to choose a different input.
We're going to talk about best practices and practical challenges. I'm
I hear you
Marco.
talking.
I work at Microsoft Research. This is just an introduction to the tutorial. So I'll be presenting this first session. And while this is a hands-on tutorial, this part will not really be hands-on. We'll try to ground.
Could you guys not hear what I was saying?
We did start to hear it, yeah.
Okay, so I guess it will work. I'll just go back to where it actually started, which is here. And then whenever we're ready, I'll just play this and I'll be here.
Hi.
Well, let me try. If I'm not on full screen, do you guys still see it as if it was full screen?
I see media playback audio buttons, so that means I'm not seeing it as full screen.
I'll put it on full screen.
I see the menu in the upper left.
Yeah, we see VLC player.
Okay. So I guess I'll do this then. Cool. I guess
Hey,
it works.
Harsha.
Hey, Rich.
Harsha, are you going to show that cool new example where you got a spike on the data set?
Sadly not. It's a nice one. Though. We have a couple hours. Maybe we can squeeze it in while you guys are talking.
Yeah. We'll give a preview puzzle. Yeah. All right. So we're still seeing your screen, Marco.
Yeah, since I'm the first one to go, I think I'll just leave it like this, unless you want to see other stuff.
So Mares is going to talk for 5 minutes. I don't know that she has any slides, but
I forgot.
Yeah.
Can you make me a co-host, by the way, Rich?
Sure.
Oh, me too.
Sure.
Yeah.
Sorry about that.
Hey, good morning. This is Xinhua speaking. Can you also check some of the email I sent yesterday for us to take some precautious activity to update the chat privilege in the room so that people can talk to host directly only?
Let's see. So I've gotten 1 million KDD emails. So which one specifically do you want me to go to?
It's email sent by Xinhua. And it's called like
Zoom conference.
Zoom logistic update. Yes. Please read that carefully because we have some lessons learned from the past 2 days, not from the tutorial of hands-on directly, but from other sessions. So we take some precautious actions to that. And at least
your new Zoom link for ADS. That's not what you're talking about.
There's a chance only MERS has this email.
Yes, there's a transpose like a Zoom bomb, so we like to be cautious. So the chat will be enabled to talk to host only.
Can you tell us the exact time that you sent that email?
Of course, just 1 second.
Sure, thank you.
I can guide you through what you have to do.
Sure.
So if you click on chat and then go to more, just select the participant can chat with host only option. That should work.
I'm sorry. So I go where? To chat.
Yep.
And then I see a huge list of participants, of course. Then what?
Yes, then there should be a more option.
I see a ... Yes, mute participants upon entry.
Yes.
Allow
definitely.
participants to unmute themselves.
No.
Don't allow that.
No.
All right, so now participants are not allowed to unmute themselves. Participants to rename themselves, I want to get rid of that as well, right?
No, you don't want them to do that, yeah.
Right. So right now, the only power participants have is mute, or the only thing that is checked here is mute participants upon entry.
Yes.
Okay.
Yeah. Is there a participant can chat with host only option?
No, I don't see that.
Okay, it's one of the other things.
I see like enable waiting room, which means I guess we have to admit people.
Oh, no, no, don't select that.
No, I wouldn't do that. There's ask all to unmute, but I assume we don't want to do that until maybe some sort of question and answer. I don't know.
Yeah.
So how do they talk back to us then if everybody is muted and we don't allow them to unmute?
I think for the initial part of the talk, I mean, until we start having like question answers, I think that's what they recommended, because people were just coming in and just playing audio and it was just becoming like really hectic.
Gotcha.
Yeah.
Yeah, that makes sense. And then should we use, when we get to a question period, should one of us go in and change this, allow participants to unmute temporarily?
I think what we can do is have people raise their hands.
I see.
And they can do it in the chat.
I see.
They should be able to chat anyways. So like, even if not audio, then.
Gotcha.
Yeah.
Hey, Harsha, you want to raise your hand and then I'll see. Well, you're one of the co-hosts now, so I'm sure you don't have a mute problem.
Right.
Yeah. We would need somebody who's a participant as opposed to. All right. Well, hopefully this will work. And the worst case is I'll enable everyone to unmute. If we can't hear from everybody.
Are we as hosts allowed to unmute people if they have, like Shenghua just raised his hand, can we unmute him? Or is that disabled?
Yes.
Yeah, so I just raised a hand and someone unmuted me because before I do that, I cannot unmute myself.
Okay.
Yeah, I just did that.
Yeah,
Great.
so if that's great. So can one of you also make me a co-host and let's see if I can enable the chat setting to be talk to host only, because that's the main feature we try to.
Okay, I've just made you a co-host, Shangzhou.
Sounds great. Let me take a look and go to the chat. And
I will be monitoring the chat anyways, so just in case people have problems.
Great. And feel free, Amia, if you need to butt in and say something, to get our attention, feel free to do that.
Yeah, okay.
I mean, it's as if you were standing in the room and you said, hey, we got a question here. Yeah, feel free to do that, of course. Yeah.
So I do see the button. If we get to the meeting setting, there was a field called allow participants to chat with everyone. So now I'm going to change that to chat with host only. So people can raise questions to all the host and co-host and can raise hand if someone need help.
Does that mean they can't chat with each other?
Yes, and they cannot send us a message to everyone publicly.
I see.
That's something we try to be cautious based on the learning in the past 2 days.
Yeah, I guess people can accidentally say something they wouldn't want everyone to know. Yeah.
Yeah, and yeah, for good or bad, that happened in the past. So that's the lesson we try to learn.
Yeah.
Okay, I will enable that, and that we can see now. Maybe some of our participants can see if you can chat with host only now. You all should not be able to see the chat to send to everyone. As a co-host, maybe you're still able to see that. Let me see. Yeah, as a co-host, I think I can still see everyone. Can
Yeah.
you remove me from the co-host and see if I can chat with you, some of you as a host only?
Happy to remove you. I never thought you should be one anyway. Okay,
That's
you're not
exactly
a
what I
co-host
want
now.
to do. Yes, you're the host.
So did it work?
Let me, I haven't checked yet. Okay,
Okay.
let me. Yeah, I think that works. Now the options available for me to send a message to as a host and also for co-host. Thank you.
Cool.
That works.
Okay, now shall I make you a host again? Like there's a chance that this will be useful, right? Are you going to be with us?
I need to check some other sessions out.
Sure,
I
sure.
will be around, but I'm not able to stay on the same session for the full time.
Completely
So
understand. What I'm going to
you're exactly right. I'm not supposed to be the host anyway.
well, I'm happy to make you a co-host again, just in case you do want to come in and help us somehow.
Of course, I'm always around in the back, and you can. We have the WhatsApp so group. Any of you pay me, I will be around to jump in to help.
Cool. So let's see. I have a call coming in.
All right.
A phone call. I'm gonna.
All right, I'm going to leave, and thank you all. Good luck.
Thank you very much for your help, Shenghua.
Of course. Bye-bye.
Bye. So any signs of MERS yet? You know, I just had a phone call coming in, a real phone call through the computer. And I'm wondering if MERS has a problem. Let's see, voicemail. Let me see if.
I'll send her a message, Rich.
I sent her an email about 5-10 minutes ago. Hopefully you can't hear this. Let me mute myself just in case, because I have no idea what this message is going to be.
Yeah, I was saying that I made like a feedback form for like this tutorial so that you can get feedback, the organizers can get feedback. So what time do you think would be a good time to send that out? I can't see.
I guess at the start, I don't really know.
Okay, no, I was just wondering if you had. Are you planning any breaks in between?
No, it's only a 3-hour. It's only 3 hours total, so we probably won't have any breaks.
Okay. I'll just use my judgment then.
We'll have some like Q&A / break.
Yeah. Okay. Sounds good.
Right. I saw MERS for a moment. Are you online?
Yeah, I also thought I saw MERS for a second. Hey, Maris, there you are. Maris, can you hear us? You're muted. Maris, you're muted.
Okay, can you hear me now?
We can hear you now. Yeah.
Perfect, okay.
Great. We think we solved the hosting problems. Scott logged in temporarily as you and then made someone else host, and then Scott logged back in as himself. So we think we've got the co-hosting all set up properly. We all seem to be able to share a screen, and we disabled some options so that people can't be disruptive during the tutorial, either intentionally or accidentally.
Okay, so something real quick. I just have 2 slides to begin the session with and just explain the agenda. I think it makes sense for me to share it with Marco so that Marco projects and then he continues with his other slides. Would that be fine?
Either way, as a host or co-host, you can also just project if you want, and then we can hand it off to Marco. Well, either way will work.
Yeah, because it's just 2, I think it makes more sense. So if that's okay, Marco, I'm gonna share it with you here, and then that would be great if you can just open them, and then I'll talk to them, and then we'll do the handoff to you.
So, and you're going to share them with Marco?
I did, yes.
Okay, you've got them, Marco? Hey, thanks to everybody who's here. It looks like we've got a good group of people. We'll start in a second.
Where did you share it, Mers?
In Teams.
Oh, I turned that off so it wouldn't bust during the...
Oh, no worries. Do you want me to?
Turn it on. No, I'll turn it back on.
Okay, sounds great.
Any luck, Marco?
It's opening. Slow.
Also, we should note that like the chat is restricted. So as Amia said, if you have questions, I think you can chat directly within, but you can't post things to the whole group. So if you have questions, send them that way.
Right, and we've been asked to turn off the ability for participants to unmute themselves. Once we get to the discussion part after each presentation, then we will be able to give people the ability to unmute if they want to do that. But apparently they've had problems in other sessions where too many people unmute at the same time, or somebody's accidentally playing music, things like that. We see your screen, Scott,
Awesome.
Marco.
Should we kick it off?
Go ahead, Maris.
Great.
All yours.
So, awesome. Thank you very much, everyone, for joining our session. We were hoping to meet you all in person, but I think this is the best we could do, bring it to your homes. So this session is going to cover intelligible and explainable machine learning, best practices and practical challenges. And it's going to also have a hands-on portion at the very end of it. The session is presented by our great colleagues, Rich Caruana, a senior principal researcher from Microsoft Research, and basically the researcher behind Explainable boosting machine. He will touch on that particular algorithm in the presentation. Then we have Scott Lundberg and Marco Ribeiro from Microsoft Research, both senior researchers, and they are the authors of SHAP and LIME respectively. And also we're joined by 2 very great data scientists, Harsha, Nori, and Samuel Jenkins from Microsoft, who will take you through the hands-on portion of this conversation and this talk. The next slide has a little bit of the agenda. We have 3 hours together. It's a combination of 45 minutes. Marco will kick that off with overview of interpretability and intro to LIME. Then Scott will take over with game theory and introduction to SHAP. Rich will cover generalized additive models and in particular explainable boosting machine. And then Sam and Harsha will walk you through InterpretML open source package, and we'll basically walk you through a hands-on experience. If you have any questions, please feel free to send them to the session moderator, and we will try to address as many as possible, but you also have our contact information. Please feel free to reach out. We are growing a community around InterpretML, and if you are interested to join that community and perhaps co-develop with us or incorporate it in your use cases, please do not hesitate to reach out. With that background out of the way, Marco, please take it away with your introduction.
And just so everyone knows, that was Mehrnoosh. She's a program manager at Microsoft
Sorry.
Research and helped organize the tutorial.
I forgot to mention that. Thank you, Rich.
Sure.
Thanks. So I actually recorded my talk, so I'll share my screen, but I'll be here the whole time. So if there's questions, you can interrupt and I'll pause and answer. And I also have time for questions at the end, whatever works best. So let me try again. We tested this before. It should work. There I am. Do you guys see this? Does it work? Can anyone confirm?
We see it, yes.
Okay, so I'll play.
Intelligible and explainable machine learning tutorial where we're going to talk about best practices and practical challenges. I'm Marco. I work at Microsoft Research. This is just an introduction to the tutorial, so I'll be presenting this first session. And while this is a hands-on tutorial, this part will not really be hands-on. We'll try to ground what explainable machine learning is and tell you why bother. And during the tutorial, we'll also be presenting a lot of different techniques. So this is kind of like a guide, so you can tell which technique should I use for what purpose and so on. So let's get right into it. If you take a machine learning course, ML 101, you'll learn that machine learning goes kind of like this. You get some data, and then you feed it into a model, maybe a deep network, maybe gradient boosted trees or whatever. And then you get some statistics like accuracy on test set, accuracy on the training set. And then there you go. You can build a product with it. And if you have high enough accuracy, you win, basically. But something is missing from this picture here. There's a lot that's missing, but one thing that's missing in particular, I'm not talking about the cash that you're going to make with machine learning. I'm talking about something else. So what's really missing is humans. In real life, humans matter quite a bit. So which humans are we talking about? So there's many of them. First, there's the ML person. So the person who's building this model. They need to understand various things like, what model should I use? What features should I use? Is my model really working? Can I trust this statistic? Can I trust this test set? So this particular human, the person building the machine learning model, matters. There's also the business or product person, assuming you're doing this for a business. So the stakeholder above, whoever he is or she. So they have to decide, should I trust and deploy this model? Is this model going to put me on the news for all the wrong reasons? So this person has to worry about this. We also have the end user. So maybe you're doing machine learning for a doctor and you have a model that helps diagnosis or something. That end user also needs to communicate with the model. So they may have questions like, why did the model say this? Why is it telling me to do surgery on this patient? Can I trust it? Should I even bother looking at this? So the end user has many questions. And finally, there's lawyers. So you may have everyone happy throughout the pipeline, but you may still need to explain things because there's requirements. For example, there's GDPR in the European Union that requires you to provide explanations for any algorithmic decisions. So there's more humans, but there's at least these ones. So humans really matter. And we've been talking about explanations, and we will talk quite a bit about them, but what is it that we mean when we say explain? So I got some dictionary definition, this definition is okay. It says it's to make an idea, situation, or problem clear to someone by describing it in more detail or revealing relevant facts or ideas. So in our case, we're not making an idea, situation, or problem clear. We're making a model clear. So the model is what we're trying to explain, or a model prediction. The someone is the stakeholders I just talked about, the end user, the machine learning person, whatever, the lawyer. So you're explaining it to someone, and that someone is going to have an impact on what your explanation should look like. So making it clear, I drew a telephone there, rudimentary telephone. So there's got to be some communication going on between the model and the humans. And the communication is going in this direction. So the model is talking to the people in here. Finally, describing it in more detail or revealing relevant facts or ideas. For that to make sense, we need to know what relevant is, what level of detail is appropriate. So for that, we need to know what the purpose of the explanation is. How are these people going to be using the explanation? That's going to determine what relevant is, what appropriate level of detail is, and so on. And so the communication that's coming out on that end of the telephone is going to be an explanation. So what that's going to look like, we're going to call an explanation type, and this will become more clear in a second. And finally, how you get that explanation is what we're going to call technique. So how do you go from the model to an explanation that serves a particular purpose? So here's a cheat sheet that I'm going to be using throughout this introduction. And so we have purpose, explanation type, and technique. And let's start with purpose because it's perhaps the most important. It's also number one. So what are explanations for? I already gave a few hints, but let's think a little more. I think that there's a few purposes or categories of purposes that encompass most of what explanations are used for. So the first kind of purpose is to augment humans. So in this case, you have a human, you have an AI, and you want the AI to help the human do something better. So you're not replacing the human, you're augmenting the human. And we're going here from general to specific in terms of information needs. So all the way to the left, very general, you may have a physician asking, how do I diagnose this disease? Very general question. Maybe you have an AI that does diagnosis, and the information you want is very broad. How do you do this in general? All the way on the right, you may want an explanation for a specific prediction. So what is wrong? So you have a model in general, but you don't want to know how to diagnose every single patient. You just want to know what's wrong with Mary. And just to make things a little more complicated, maybe you have, why is Mary suddenly bleeding? And the reason I put that there is because this creates a time constraint. So the level of detail that's appropriate when there's a patient bleeding is different than if you have a doctor in her office looking leisurely at explanations and trying to do a diagnosis. So in those situations, the explanation maybe will change. Similarly, you can also have a judge trying to decide, should I grant bail to John or this particular person? And that's also very specific all the way to the right. Anyway, the point is that human is making the decision here at the end. I think I have one more. Yes. As an end user, you can ask, should I buy this book? Like this machine learning system is making a recommendation. Should I go ahead and trust it? Obviously, the stakes are lower there, but still very specific. The point is the person who is the one who makes the final decision. The model is just making suggestions and helping the person along. So this is augmenting humans. The second type is to help humans evaluate the AI. And this is very common. So you have an AI, you want to know if it works. So you use explanations to understand what it's doing. And this is a great use of explanations. On the general side, you can ask, can I trust this AI? And this is a very general question. In general, is it behaving appropriately? Maybe towards the middle, you can ask a more specific question, but still somewhat general. Is it racist? However you define racist, is the AI racist? And explanations can help with that. And then finally, if you want to get GDPR compliance, you may need to explain every prediction. So for the purpose of evaluation, you may need to go and see, you made this prediction, why did you make this prediction? So that you can audit the AI. So this is still evaluating the AI. And that leads us to the last purpose of explanations, which is to help humans improve the AI. So obviously evaluating and improving go hand in hand, but you may have some more specific information needs in here. For example, you may not ask, which segments of my population does my model struggle with so that I can go and fix them? You can ask, does it work when there are typos so that I can go and fix them again? So these are more focused questions. And then you may also want to ask, like, why does this happen? So this is a famous case where Google had this, I think she was a Harvard professor. And if you Google her name, you got all of these ads for this person was arrested, public records, and so on. And you want to understand why that is happening so you can go and fix that, because that is a very bad thing for PR. Anyway, so three general kinds of purposes. A lot of things fall into those. So augmenting humans, evaluating the AI, and improving the AI. Now, even within one of those, you may have more specific or more general questions. And it's useful to keep this in mind when you're thinking of explanations. That's it for purpose. In terms of explanation type, there's lots of different explanation types that we could show the user. So I'm going to use an example to display a few of them. So the example he's predicting income. Let's say that I have some census data and I want to predict, given an AI, if a person makes more or less than $50,000 a year. So you get a prediction for X, person X. What can explanations look like for this particular problem? And again, I'm going from general to specific. So I'm going to show what the explanation looks like and then put it on the general to specific line. So the simplest kind of explanation is to just show the whole model. So if your model is very simple, like a decision tree, you can say, here's my model. And there you go. You're explaining everything at once. So this would fall all the way on the left on the general side. So this is common. This is used, like you can use a linear model decision tree or something like that. Another kind of explanation is to do feature importance. So you don't want to know how features are used, but you just want to know what features are being used, how important they are. So global feature importance. And there's techniques to get this. We're not in the technique side yet, but the point is that you get a ranked list of features saying, these are the features that the model thinks are most important for this task. So maybe job type, education, how much capital gain they have, and so on. Again, this is very general because we're not talking about specific predictions. Another kind of explanation is if you look at one specific feature, in this case, education, you can look at the impact that it has in the predictions. So if as you change education, how do my predictions change on average? And see, in this case, it happens what you would expect, it goes up. This is what you would expect if you get more education, probability that people make more money goes up. So this is called a partial dependency plot. It's a little less general, but still pretty general. You're looking at the whole data set, but one feature at a time. You also have what I'm calling here slice statistics. So instead of just getting overall statistics, accuracy overall, you slice your data in particular ways. So for example, you look, how is my model doing for men and women? How is my model doing for people in different countries, for example, United States, Brazil, India, and so on. Or you do whatever slices you want, and then you get, this is a kind of explanation, you get accuracy over the slices. Still very general. Now, all of these are not specific to individual predictions, so I'm going to put a line here, and now we're going to talk about a different kind of explanation types where you're explaining individual predictions. So let's say I have one guy, DOG, and the model predicts that DOG makes less than 50K, and I want to understand why. What kinds of explanations can I look at? So that's why I have a dotted line there. So the first kind of explanation you could have is an anchor. It's still very general. And an anchor is saying, look, if this condition is true, you get this prediction. So if the person, for example, only went up to high school, doesn't have a college degree, this particular model will always predict that they make less than 50K. And that's why it predicts that DOG makes less than 50K. Clearly a mistake here. But it's a somewhat general explanation. You're explaining DOG, but you can easily generalize that to a lot of other people who did not get a college degree. So it goes in there. Perhaps the most common type of local explanations is a local linear model. So you're giving a list of pros and cons. So DOG, here's why I think he makes less than 50K. Here's information that perhaps makes me think he may make more than 50K. So he doesn't have a college degree, but he works a lot, but his past retirement age, so I think he makes less than 50K. So this gives you insight. It's a little more specific, but it's a kind of explanation. Another kind of explanation is instead of telling you why I made this prediction, I show you what would make the model make a different prediction. So this is a counterfactual explanation. So in this case, it's saying, look, if you added college to BOG, I would have predicted that he makes more than 50K with 88% probability. So this is a counterfactual explanation. And then finally, this is a very different kind of explanation. You're not looking at BOG in particular, but you're looking at the training data and saying, these are the people that most influence my prediction of BOG. There's these other people in my training data that I think kind of look like BOG. And then you say, this is, you look at them and you try to understand why the model predicted less than 50K. So this is just a sample. There are many more explanation types, but I just listed here 8 different types of explanation. How do you decide which one is best? If you want to use explanations, what should you use? And the answer is, it depends. So let's say that you're business analysts and you're trying to decide what are important predictors of income? Or maybe you're a researcher, you're trying to decide just what are important predictors? What would you want in this case? Well, I think you'd want a feature importance, global feature importance, because that is precisely the information you want. You want to know what features matter for predicting income. You're not interested in specific VUGs or whatever else you can think of. You're not interested in slice statistics. You just want to know what features are important. However, if you want to know if your model is fair, and let's say you want to know if your model predicts differently between men and women or different races and so on, then what you want is clearly slice statistics. Feature importance may help you. You may want to use both. A partial dependency plot may also help you, but most likely what you want is slice statistics. Now, if you are BUG himself and you want to know how do I make more money, or a more serious case, if you got your loan denied and you want to know how do I get it approved, then what you want is a counterfactual explanation. So clearly it depends on the purpose, and that's why I spent all of that time talking about purpose of explanation. It also depends on how you can get these explanations, and this is the next part. Like sometimes it's hard to get particular kinds of explanations, but in the very least, it depends a lot on what you're going to be using explanations for. So that's it for explanation type. Talk briefly about a bunch of them. How do you actually get these explanations? And this is what I'm calling technique here. And we'll be very brief on this. So how do you get explanations? So let's say someone comes and says, can I please have interpretable machine learning? How do you do it? And I want a linear model. I want a list of pros and cons. That's what I'm comfortable with in terms of explanation type. How do you get them? There's two kinds of approaches. One is to do interpretable models, and the other one is to do black box explanations. So an interpretable model, what you do is, do you want a linear model? I'll train a model, like a linear model, that can produce that kind of explanation. I cannot train, if you're doing an interpretable model, I can't train a neural network because I cannot produce linear explanations from a neural network. I can't train a decision tree because that's not going to give me a linear explanation. And Rich, who is going to be giving a talk later on, has a lot of research on this camp. As for black box explanations, me and Scott, who is also going to be giving a talk later on, would just say, bring your model, whatever it is, and we'll explain it with a linear model. So it's you treat the model as a black box, and there's pros and cons to that. So a few pros and cons. So interpretable model is exact. If you're using a linear model, the explanation that you get is the ground truth. It is what the linear model is using. Whereas if you bring me a neural network and I say, here's a linear model, that's going to be an approximation. It's not going to be exact. It's also fast. Like if you know what the model is and you can peek inside, typically you can get explanations that are much cheaper than if you're doing black box, where you have to perturb examples to get at what the model is doing. However, if you do black box explanations, it's not that the explanation is more accurate, but the models that you can use tend to be more accurate than interpretable models, at least up to this point. And it also is more flexible. So this is what I mean by flexible. Let's say that the person changes their mind and now they want an anchor explanation, but they want to use the same model. Rich would have to say, well, we're going to have to train a different model that can produce this kind of explanation, this kind of rule-based explanation. Whereas me and Scott would say the same thing. Just bring your model and we'll change explanation technique. And you can explain different models of the same technique so you can compare them and so on. So there's more pros and cons. Here's another example. If a doctor came to me and said, can I trust AI to diagnose my patients? Basically, can you replace me? Rich may say something like, sure, just give me a few more years and we'll have an interpretable model ready to go. I would be very skeptical that a black box explanation would be able to make sense here. Like the reason is I would not want a black box doing diagnosis. I don't trust it, even if I can provide some explanation. I don't know what Scott would say. You can ask him later. He's done a lot of research on medicine and explanation. But the point is that as you get to high stakes, perhaps you want an explanation that's exact. Like you want to make sure that what the model is doing is exactly what you're telling the user that it's doing. There's also another trade-off between accuracy and interpretability. I alluded to this a while ago. And typically this is the plot that people show, and I think it's accurate. It's a cartoon, but I think it's accurate. All the way on the right, if you want models that are very interpretable, they tend not to be very accurate. So if you have just a linear model or a short decision tree, they're very interpretable. You can look at them and get a whole model explanation, but they're not very accurate. And the way we make them more accurate is we make them less interpretable. So we take a linear model and we add millions of features with combinations of features so that it's hard to interpret it at that point. Or you take a decision tree and turn it into a random forest with thousands of trees, at which point you can't interpret it anymore either. So there's some research on interpretable models, and Rich is going to present some of that later. And there's some models that we have that are pretty accurate and are still interpretable. But in many domains, not all, but in many domains, they're not accurate enough for real world use case. Whereas if you take deep learning or ensembles, they are very accurate, even though they are very opaque and not very interpretable. So at this point, they tend to be more accurate, at least for domains like vision or text. So sometimes they can even be almost as high as human level accuracy. So what are our options here? Well, again, we can be model agnostic and say we're going to do black box explanations so that we ignore the internal structure of the model and produce explanations. And I'm partial to this approach, me and Scott, as I said before. Again, you can explain any existing model, even future models. You can compare two models. You can adapt explanation to the target user. So there's many advantages here. And what you get in this plot is you move everything to the right. You make everything interpretable. But there's also the other approach of creating interpretable models, where you take these models and try to make them more accurate. And the benefit here is that if you can do it, it's very hard, but if you can do it, the gains in accuracy tend to be real. Because if you do an interpretable model, you tend to avoid shortcuts. A lot of times these deep neural networks or ensemble models are very accurate because they rely on spurious correlations and shortcuts that we don't want to rely on. So that's why I'm calling it real accuracy here. If you can get an interpretable model to work, it tends to be more trustworthy. So again, there's trade-offs back and forth. But as far as techniques, these are two different camps, two different families of techniques to be aware of. And again, it depends on what your purpose is. If you need an exact explanation, you're going to have to go with an interpretable model, pretty much. Now, let me touch briefly on one type of black box explanation called LIME, which is in this paper that we published in 2016. And the reason I'm presenting this in a little more detail is because many of the principles here apply to other techniques as well. So I think it's good to get a handle of them on them. So again, we're explaining individual predictions. So this is a complicated model in 2D. The global explanation is too complicated. And that's our assumption. We're saying, look, we're using a complex model because we want something that is not super simple. Otherwise, we just use a simple model. So if the global explanation is too complicated, what are we going to explain? An individual prediction. So remember, I was explaining BOG before? That's what we're doing here. So that allows us to zoom in until the local neighborhood looks simple enough that you can explain it. So I may not be able to explain how income works in general, but I can explain why the model thinks that BOG makes less than 50K. And that's an explanation there. So the explanation is locally faithful. It's not explaining everything, but what it is saying, it should be faithful to the black box model. So what does an explanation look like? For LIME, we use linear models. Here's an example application that I use later on. There's this classic problem of predicting whether an email message goes to different news groups. And we took a subset where we have atheism and Christianity. And we trained a model, and the accuracy of this model is very high, 94% test set accuracy. So you may think this model looks good. Let's look at some explanations. This is what the explanations look like. This is an example. So this is an email that says, I think Christianity is the one true religion, blah, blah, blah. Clearly an email about Christianity, but the model predicts atheism. And the explanation should show you why that is. So the explanation here is the list of pros and cons. It's a linear model, the most common type, as I mentioned before, of black box explanations. And what it's going to do is it's going to give way to different words. So it's going to say, look, Christianity is really positive towards the prediction of Christianity. But posting, host, and keef are very positive towards atheism. And that is why I predict atheism, because of all these words. Clearly, there's something fishy going on because posting, host, and keef, we know, have nothing to do with atheism. So the model is relying on some shortcuts. And on second thought, you may think, I don't want to trust this model. And you should not, because the model is picking up on various kinds of shortcuts. So the explanation displays that. And here's a few shortcuts that it's using. So key, for example, in the training set, it's always in the class atheism. It's always in emails in that atheism news group. And that's just a quirk of this data set that shows up both in the training set and in the test set. So if you're training a model and you see the word Keith, you can always predict atheist no matter what's in the email, and you're going to do very well in terms of test set accuracy. Of course, that's not going to generalize. So LIME is short for local interpretable model agnostic explanations. How do we get these explanations? Here's how we get them. So we have an original example we're trying to explain X. What we do is we sample a bunch of points around X. So we create perturbed samples, like we change X in different ways, and then get predictions from the black box model. And this is the case for most black box techniques. You have to perturb examples because you don't have access to the internals of the model. So you get predictions. And remember, we want to be locally faithful. So for LIME, we weigh the samples according to how far they are to X. So samples that are very close to X are going to be weighted very highly. Samples that are far are going to be weighted lowly. Because we want our explanation to be accurate close to X. We don't care if it's kind of inaccurate far from X. Then we learn a simple model on the weighted samples and use that model to explain. So like a linear model. Now I've been talking about explanations, but there's something we call an interpretable representation. Again, this is general, not just to LIME. And it's as follows. Maybe your model works on embeddings. You don't want the explanation to be presented in terms of word embedding or BERT embeddings or whatever. You want the explanation to be in terms of words. And that's what we call an interpretable representation. And that's what we perturb, and that's what we explain. So interpretable representations are important to think about. For images, what we did, so the original representation is 3 color channels per pixel. It's a grid, it's a matrix. But what we do is contiguous superpixels. So we divide the image into different parts and say, is this part turned on or off? And that's easier for people to understand. So here's an example of what that sampling looks like for images. Let's say I have this image and the model, I want to understand why it thinks there's 21% probability of a Labrador being there. What I do is I perturb that image. So I hide parts of the image and then get predictions. So if you hide the guitar, it thinks it's Labrador. If you hide the Labrador's face, it doesn't think there's a Labrador, and so on. And I do this enough times that I get a data set that I then weigh according to how far they are to the original image, and I get an explanation that looks like this. So this is saying, I think there's a dog because of the dog's face, basically. Now, this is explaining individual predictions. What if you want something more general? If you want to explain the global behavior, one approach you can take, for not just LIME, but for any black box technique, is to explain the global behavior by looking at a set of explanations. So LIME is explaining a single prediction. We're going to look, you just get insight into that region. What we're going to do is pick K explanations to show the user. So you want a representative set so that you get a global picture, and you want something to be diverse. So if you have the black one, you don't want the red explanation to show up because it's very similar. You want something like the green one. And we don't need to go into the details. It's done by submodular optimization, but we call this submodular pick LIME, where we're showing K explanations, and this is going to be important in the example. Now let's get back to this cheat sheet. I told you about one specific technique, LIME. It's very specific. I'm explaining individual predictions. It's a linear model, and it's a black box technique. So whenever you see a new explanation technique, you can think about this grid. Where does it fall on this cheat sheet? And LIME falls in here. So we did some experiments, and whenever you think of experiments, you should think purpose. What is this experiment trying to evaluate the explanation on? And for LIME, we did 2 things. We did evaluating the AI and improving the AI. So how did we evaluate the AI? We had this fun experiment where we told people, we trained a model to predict between wolf and husky, and it's supposed to be a hard task because they look alike. What we didn't tell them is that, so we told them the model is very accurate, but we didn't tell them that the model is actually just predicting snow. So whenever it sees snow, it predicts wolf. Whenever it sees something with a different background, it predicts husky. And we're not interested in this model per se. We're interested in whether people would notice. And these are machine learning experts. Do they notice that we just have a deep snow detector? So what we did is we showed people a bunch of predictions and then asked them 2 questions. Do you trust this model? And what is the model doing? Like, how is the model distinguishing between wolves and huskies? And then we show them explanations and ask them the same questions again to see if they got the insight. So here's the results. Before explanation, most people, thankfully, did not trust the model because they only saw a few examples, but 40% of participants did trust the model. And less than half of the participants got this no insight. And we're being generous here. If someone even mentioned the background or snow as a potential feature, we said that they got this no insight. So more than half of the participants, these are machine learning experts, did not realize that the model is basically worthless. It's not distinguishing between wolves and huskies at all. After seeing the explanations, basically nobody trusted the model and everybody got the insight. And the people who didn't probably didn't understand what was going on. So explanations help people get insights and avoid this kind of mistakes, even experts in machine learning. So that's evaluating the AI. We also did a couple of experiments on improving the AI. And so one way of improving the AI is to do model selection. And what we did here is very simple. We asked people in Mechanical Turk, so these are people with no machine learning expertise at all, to see different predictions and pick which model would generalize better. So again, this is atheism and Christianity. They see a prediction and then they see an explanation and they can judge which model is doing something that's more sensible, even though both make the same prediction. So we're measuring how often they pick the model that generalizes better. If they just guessed, they would have picked the right model 50% of the time. With random line explanations, they do it 75% of the time. So this is just looking at random explanations, 6 random explanations. But if we do the submodular pick that I mentioned before, where we try to be representative and diverse, they pick the right model 89% of the time. So even Turkers can do model selection pretty well, at least for this particular test. We then ask, can they fix the model? So this model is not working very well. It's not generalizing. Can they fix it by very simple feature engineering? So here's how we did this experiment. We have the data set, we have the model, we show explanations to people in Mechanical Turk, and we ask them to give feedback on the explanation. So we ask them to say, look, these words do not make sense. Please remove them from the model. And that's it. They just tell us these words do not make sense. And we retrain the model, removing those features, and do this again and again for a few cycles, 3 cycles, basically. So we repeat. And then we test this on a new data set that Turkers don't know about and see how well do they do on generalization. So here's the results we got on this. If you just trained on 20 news group, the model does not generalize at all to this new data set. It gets 57% accuracy. If you train on a hand clean version of 20 news group where you try to remove, I personally try to remove these biases and stuff so that the model will be accurate, you get much better generalization. And this is a result if you do this procedure I just described where Turkers are clicking on explanation. So as the rounds get by, so after 3 rounds of explanations, they get 75% generalization accuracy. So this is very good. And just for each round took about 3.5 minutes. So this is 10 minutes of feature engineering, roughly, and people can get a model that generalizes much better than if you didn't do something like this. So and again, these are not experts. So we try to show that explanations can be used to improve the AI, and there's many more experiments that other people have done and so on. Anyway, let me get back to this cheat sheet. I'm about out of time, but our tutorial is going to cover many techniques, different black box techniques like SHAP, who Scott's going to be presenting, and other techniques, and also interpretable models, GAMs, and so on. So we're going to give you a broad overview of different techniques, but we're also going to give you the practical details. So how does the code work? How do I apply this? What are the trade-offs in terms of time? And how easy is it to use this? We have this set of tools at Microsoft to make the process very easy. What if I want to compare between different explanations? How do I do that? What kinds of visualizations can I get? But I thought it would be good to give you this overview first, so that as you see the different techniques, as you think about what makes sense for a particular application, you can think, what is the purpose? Before you can answer which explanation is better, you have to figure out, why am I using this explanation? Why do I want explanations in the first place? And then you can think about different explanation types. Do I want a linear model? Do I want a partial dependency plot? And that is going to inform whether you should use an interpretable model or a black box technique, and which of them you should use. That's all I have. I can take any questions you guys may have, or we can take a break as well. Thank you.
Right. Put some headphones on here.
So there were a few questions in the chat. I don't know if you want to look at them, Marco, and possibly answer one or two of them, or if we want, we could unmute people if we don't think that's too dangerous. Any suggestions?
Let me look at the questions on the chat first. Question. I have a question about attributing a prediction on an image to pixels. Line makes sense and people also use gradient map. Which one is better? So again, the answer to this question is going to be what I answer to every question of this kind, which is, what is the purpose? What do you want the explanation for? So if you care about specific pixels, if you care about how predictions change depending on specific pixels, then you should use pixel-based explanation. If you care about regions in the image, then maybe you should use something like what we did, superpixels, which I think tend to be more interpretable. But if you care about something else, like it really depends on what your purpose is. If you're doing radiology versus ImageNet, that's obviously going to impact which one is better. So there's no, I think it's hard to say this is better all the time, because usually it's not. And I have another question sent to me privately. Can I use Lime to explain predictions on time series data? You can, like the framework is general enough to be applied to time series, but it's a little trickier because you have to figure out, I talked about interpretable representations. You have to figure out what the representation is and what you're going to be perturbing. So if you have a time series, do you consider a feature as one feature throughout, or do you break it up into the different time steps? Do you want the explanation to be this feature is important, or this feature at this particular time is important? And that's obviously going to impact the kind of explanation that you get. Like if a feature is only important at one particular time and you want to know that, then it's much more expensive because you have to perturb that feature across time. So I would say that it's not trivial to use Lime or any other explanation techniques for that matter, because it's hard to come up with an interpretable representation. Another question. What is the scalability of black box methods like Lime? If I have very high dimensional data, will Lime still be able to generate insights in a reasonable amount of time? So it depends on a couple of things. So one, how high dimension is it? And two, how expensive the model is, the black box model that you're trying to use. Because generating the perturbations is typically not very expensive. It's getting predictions from the model that's expensive. So if it's a tabular model, typically those are cheap. Like you can get a bunch of predictions, you can get thousands of predictions per second, then it will probably scale. If it's an image model where it's taking you maybe, you're doing maybe 5 images per second, and it's very high dimension, and then you don't use like superpixels, then it's going to be very hard. I know that Scott has done a bunch of optimization in his work, like on Shap, to make it much faster. So I think it probably is the case that Shap would scale way better than Lime for almost anything. So you should try that if you have something very high dimensional too. I think that's all the questions I have there. If there's any more questions, either raise your hand or chat or whatever, or we'll take a break. Actually, we won't take a break because Scott.
Thanks a lot, Scott. That was great. So wonderful introduction too.
I'm Marco.
Marco, excuse me. I'm thinking Scott is next, and of course.
Wait, someone has their hand up. Should we take one more question?
Sure, go for it.
I don't know how to unmute them. Will it?
I think we can ask them to unmute.
Okay. I asked you to unmute.
Okay. Can you hear me?
Yes.
Cool. That seems to work. Thanks. There was a session yesterday about fairness in ML and AI, which was extensive, and they touched on a number of tools for that, including FairLearn, which is at Microsoft, and as long as Equitas and a number of other ones. How do Lime and Shap? How does the concept of interpretability integrate with the concept of fairness in AI, and maybe particularly with some? I'm curious to know how that integrates with like the tools that exist for measuring fairness in outcome at this point.
Yeah, I think, again, it comes back to purpose. Is the purpose just to measure? If you have a specific measure of fairness that you want to measure, then you should just go and measure that directly. And that will obviously be better than taking the roundabout way of getting an explanation and saying, oh, it doesn't look like it, and so on. But typically, like if you want to get insight, then explanations come alongside those techniques that have specific metrics and so on. So that I think Scott has a few fairness examples on his talk that go beyond just saying this feature is important, like race is important, where explanations show other behaviors that would perhaps remain hidden if you just use a metric that show up in explanations. So I'll wait for him to give a good example of that. But in general, my answer would be they're complementary. Like you should, if the goal is fairness, obviously the fairness specific tools are your go-to at first, but I don't think explanations are irrelevant at that point. They're still relevant.
And I'll also give a brief example of bias in recidivism prediction.
Thanks.
There's a few more questions. Should I stop, or is it okay, Scott? What do you say? 3 more minutes?
Go ahead.
Cool.
Good.
Can Lime still work with transductive models, or models need to be retrained with new data points? Good question. I haven't thought about that. I don't know what an explanation would look like then if you have a model that's constantly evolving. It seems to me that the explanation would be outdated. Like if your model is learning online, like you'd have to put a stop and say, I'm not going to learn from this perturbed samples. So you get a snapshot. This is what the explanation is doing right now. Question. Several works address the problem of adversarial attack to explanation methods. How do you feel about that? Is it worth investigating towards this direction? In general, I think that adversarial stuff is a concern if you're using explanations as ground truth for something. Like if you're saying, I'm going to use explanations, and if the explanations are good, I'm going to go ahead and deploy my model, and that's it. Like if you're using them in domains like that, and I don't think you should. So I'm not very concerned about adversarial attacks because I don't think explanations should be used in that manner. It's an interesting area of research to understand because they give insight not only into adversarial attacks, but into what can go wrong with explanations, even in a non-adversarial setting. But all of the work that I've seen is stuff that's very contrived that would not happen unless you're trying to make it happen. Question. Question about the implication of model performance and explanation. Do good models generally have better explanations compared to bad ones? For example, if a linear model performs really bad in terms of goodness of fit, the explanation probably also does not make much sense compared with explanations from a black box model that performs better. So that may be true, but if the model is relying on, if the model is bad, then your explanations typically will also be bad. But if the model is good, explanations can still be bad if the model is relying on shortcuts, like the example I showed before. That model that I showed had 94% cross-validation accuracy, but the explanations made no sense because it was relying on shortcuts. Question, are Shapley value-based explanations stable? As in, if you change the input slightly, does the output change a lot? I'll let Scott answer that question in his talk. So you should save this question, Scott. He's the Shapley person here. And then last question. When does Lime give misleading explanations? If it's giving a series of misleading explanations, how can you tell without being a domain expert? I like this question because it is the case that sometimes you get explanations that are incorrect, meaning they're not faithful to the model. So this happens in a couple of situations. One, when your interpret representation is not flexible enough to capture what the model is using, your explanation is not going to get at what the model is doing. So for example, if you're using superpixels and we're hiding superpixels, and your model is in fact looking at colors in the image, you're not perturbing the color, so you're not going to be able to know that colors are what's important, like red on the right upper corner as opposed to green is what's important. Like you're not going to be able to get that insight. So that's one. Another one is even when zooming in, the model is very nonlinear. then even locally, a linear model is going to be a bad approximation. And both of those, typically you can tell if you see the fit, like you can look at the explanation, how good does it approximate the black box model in that neighborhood? And you can get a score. And if that score is consistently poor, then you can tell something is off here. The explanations are not, this technique is not working, and you have to diagnose that. Those situations are rare. I have seen them, but they're not as common. And I guess I'll stop here because I already ate too much time from Scott's talk. Sorry, Scott.
That's great,
everyone.
Marco. Thank you very much. Hey, Scott, are you ready to go?
Yep, all set. And for some of the questions that are relevant, we'll dig into those afterwards. And just for the clarity on time, Rich, I think I'll try and hit 10:30 to flip over to you. So I'm going to start with a set of slides, and then if we have time, I was going to jump over to a notebook to try and be fairly hands-on and make some concrete stuff. But I do want to save time for questions because I think that's a valuable part of this format. So if someone could confirm once I get the screen sharing and everything is looking like it should. Let me
Not yet.
share. Yeah, I'm just hitting
It's coming
share.
in now. We can see it.
Okay, great. I'll end up in presentation mode here. Okay, great. So I'm going to cover Explainable AI with Shapley values. So this, Mark gave an excellent overview of all the different aspects of explainability and the different techniques and applications. Here we're going to focus on a particular area of explainable machine learning, which is connected to game theory. So when you're trying to do credit allocation, either global credit allocation, so like the global feature importance type stuff, or local credit allocation, like a linear model, it turns out that you can draw some strong parallels to ideas in cooperative game theory. And that's useful because they have studied notions of fairness and fair credit allocation. And those notions of fairness that apply sort of in the abstract to these theoretical games also apply very well to machine learning models. So some of you may be familiar with this, so the rough ideas behind Shapley values, but I'm going to go over them fairly briefly here, just to make sure that we're all on the same page. And then what I want to do is try and take this a bit more practical and look at example scenarios and just talk about how do we use these in practice. What are the intuitions we should have as we use them? How do they map to some of the scenarios that Marco was talking about? And just really kind of be concrete about it. So here's in the interest of being concrete, I'll start with a simple scenario here, where whatever type of model we're talking about, we're going to view sort of a black box explanation perspective here. We have a model and we have some information about a sample coming into the model. In this case, that sample happens to be a bank customer. And the model spits out some outcome that we care about, in this case, risk for repayment problems. So as Marco mentioned, there are a lot of stakeholders involved here. You have the ML scientist who's interested in evaluating the AI. You have the customer who is interested in explanations, perhaps even based on legal requirements. And you have the people responsible for the financial decisions that are being made, and they want to understand what's their financial risk. All these things are very important questions that need to be asked of this model, and all can be supported in various ways through explanation in general, and specifically through Shapley value-based feature attribution. So Marco talked about interpretable representations. When we're talking about Shapley values, we're talking about an interpretable representation that involves a toggling. It involves either showing a feature or hiding a feature from the model. This turns out to be a very, very common way to manipulate a model. So if we think about how this might work for John in this scenario, if we hide all of the features from the model, what we're essentially, one way to say, what does it mean to do that? Is to say we don't have any idea what any of John's features are. And so that we're just going to take the expectation over some background distribution, which could be our training data set. It could be the set of all people whose loans was accepted. This choice of prior in our mind is important to think about. But whatever it is, we're going to take an expectation over it. In this case, that produces a base rate of 16%. So this is what happens when we know nothing about John. And then what we're going to do is explain how we got from where we know nothing about John to when we know everything about John. Okay, so John's prediction from the model was 22% risk, but the base rate, if we knew nothing about him, was 16%. So what we really need to do to explain what was specific to John is how we got from 16 to 22%. And we can do that by starting at the base rate and sequentially introducing features into the model. And by introducing, what we're going to do is actually just setting those features equal to John's values. That's what do means. It's like, if you're familiar with causal notation, that's literally do calculus notation, where there's a paper you can look into. But essentially what we're doing is we're taking each feature of the model, in this case, the fact that his income was not verified, and we're setting that. So we're not taking the expectation over that feature anymore. And then we note that when we do that, the expectation changes. It goes up by a little bit. And that means that having his income not verified increased his risk from 16 to 18%. We can repeat this for his debt to income ratio, the fact that he was delinquent 10 months ago. All of these things, as we learn them about John, increase the output of the model, so increase his risk. Then we learn that he has no recent account openings, meaning he hasn't applied for credit recently. And this is an actual model trained on some data set for lending. We notice that that actually drops his risk significantly down to 18%. And then we see that he has 46 years of credit history, which perhaps counterintuitively raises his risk back up to the final score. So at this point, we've seen all the features of the model in this simple model, and that has explained how we got from when we knew nothing to when we knew everything. So we've essentially allocated that delta among these values. And these phi values, phi1, phi2, phi3, these are the Shapley values. Except there's a little bit of a complexity here. And that is that the order matters, right? I can't just add features one at a time and expect the order to be arbitrary, because that would work if it was a linear model. But if there's any sort of interaction effects, those interaction effects will not show up until I see, if it's a pairwise interaction, the second feature, for example. So to take a look at that in this particular model, we can look at the no recent account openings and the 46 years of credit history. Those are two features about John. And I first learned that he had no recent account openings and then learned that he had a long credit history. But I could easily first introduce the credit history feature and then the account openings feature. And it turns out if I had done that, something very different happens in the model. Okay, and that's because there's a strong interaction effect between having a long credit history and any recent account openings. So this means we can't just, blindly introduce things and call ourselves done. We have to think about trade-offs that are going to need to be made when we approximate complex models with additive measures of importance. So, and that's when it's helpful, I think, to look back at work that's been done even in the 1950s on game theory by a man named Lloyd Shapley, who actually won a Nobel Prize a few years back for his work in this area. And he derived a set of fair allocation principles, which led to these values called the Shapley values, named after him. And they're very easy to state in this context. They simply result from averaging over all n factorial possible orderings of introducing features one at a time into your model. So that's super easy to state, very hard to compute. In fact, they're NP hard in general. And so that has led to a variety of research approaches to try and make these practical for machine learning applications. And I could probably talk for hours on all the different ways that that has been done, some of which I've done and some of which others have done. And the package that I help maintain called SHAP is in large part, the contribution of that is a collection of methods to do this more efficiently for models. So we can compute them exactly in fast algorithms for specific model types, including tree ensembles and things like that. And we can approximate them pretty well for other model types. So I'm going to skip all over the computational side of this and how we can make them practical, and instead just use the practical methods that we've developed and tell you how I found them helpful and how I think we can use them as tools in the machine learning process. So the first thing is to kind of consider what is it we get when we run these Shapley values on a model across a whole data set. Okay, so here we have On the left side, a data set. So we have, imagine a tabular data set, okay, just to keep everything nice and clear. We can talk about more complex ones later. But imagine we have a nice tabular data set. It's got a certain number of features, which are our columns, and a number of samples, which is our rows. And then what we could do is plug it into, for example, tree explainer if we want, which is just one of several of these algorithms. And when we produce local explanations, it's important to remember that we get another matrix out. And that matrix is of the exact same shape as the input matrix that we were given, that we passed into the model. But now the units of the input matrix, of course, were dependent on the features themselves, right? So some of the units were categorical, some of them might have been dollars or years. But the values sitting in the blue matrix here, the Shapley values matrix that came out of the Shapley value computation, this matrix is now filled with values that are in the units of the model's output, okay? So this essentially is telling me how much each feature mattered. And what I'm gonna talk about next is what can we do with this blue matrix on the right? Because it turns out that there are a lot of downstream tasks that can be enhanced by looking at this matrix and slicing it in various different ways, okay? And if you were to, for example, just to connect back to what Marco introduced in the overview, if you were to take sort of the mean absolute value of these features over each column, so you're going to average over all the rows, you would get a global feature importance. If you were to slice out a single row, you would get a local feature importance. If you were to cluster them, you would get something in the middle. And I think there's a lot of interesting things we'll do with that. So let's start down that road. But before we do, I wanted to briefly highlight the fact that interpretability is not always best with simple models. And that is, there's an interpretability cost that comes with model bias. So I think all of us are familiar with the, actually, I think I have a flip over of a slide, so I'll skip forward. So I think all of us are familiar with the problems that come when you have a highly constrained model. Okay, a model that is linear when your data is not linear. We realize that that bias in our model, when it doesn't match the true structure of the data, will cause a decrease in accuracy. But it also has an impact on interpretability, and that's what I want to talk about here. So what we can see here is a real data set, okay, of a bunch of features, including BMI and age, and a simulated outcome of mortality risk. Okay, it hardly matters what it is, but it's a binary classification task. And what we've done is when we simulate the risk of some of this outcome, we started it being a linear relationship between BMI and age, and then we changed the outcome variable to depend more and more quadratically on BMI and age. So you can see the contour lines become more and more curved as we go from left to the right. So essentially we're increasing the amount of nonlinearity in our data, in the relationship between our input features and our output. And if we do that, what we can look at is how does a linear model versus, for example, a gradient boosted regression tree, in this case XGBoost, do as we increase the nonlinearity. So what you'll see on the y-axis here is the loss difference from the true model. Okay, so we know that everything is all simulated scenario and the outcomes. So we know the true loss of the model, and we can see how close do we get to that. So purple is the true model, and the blue is a gradient boosted decision tree. And you can see that there is a small gap, and that comes from essentially the price paid, bias variance trade-off. So you see that variance penalty paid by XGBoost. However, you'll notice that it does not pay much of a bias penalty. Okay, so the linear model on the left has no bias mismatch, but the linear model on the right has a very strong bias mismatch with the data because the relationships are no longer linear. And so we can see the increasing loss of, on the red lines, the linear logistic regression model. Okay, so a linear logistic regression model turns out to have, not surprisingly, decreased error, decreased accuracy as we go to the right, and hence that is accuracy that's lost due to the bias. Okay, so this is probably something you're all familiar with. But what I want to focus on here is the fact that there's something else that's been lost as well, and that's explainability. So just like you can lose accuracy due to bias, you can also lose explainability due to bias. And that's because what happens is as the linear model begins to not fit the true structure of the data, it will try and compensate by leveraging slightly correlated features that happen to be related in a perhaps nonlinear way with the true feature in the model. So in this case, we know BMI and age are the only features that drive the outcome. All the rest from this, medical data set, we didn't use in simulating the outcome. However, as we increase the nonlinearity between BMI and age, the linear model begins to reach out and depend on very complicated cancellation effects between irrelevant features. So you can see here, the y-axis is the percent of weights. That's the percent of the coefficients of the linear model that are assigned to irrelevant features, or in the case of XGBoost, the percent of their shot values. So XGBoost never reaches out for nonlinear, for irrelevant features because it doesn't have a bias mismatch, but the linear model does. So I think it's important to remember that if you train the linear model and that linear model does not match the true data generating mechanism, you may be able to fully understand how that model is behaving, but that model's behavior may not reflect at all the actual structure in the data set itself. So I want to present this as a compelling motivation for why you should strive to use lower bias models versus high bias models, even in cases where interpretability is paramount. So I think, Rich will probably talk about this later, but I struggle to think of cases where you should be using a linear model on continuous inputs if interpretability is important to you, because it's very hard to guarantee that you do not have strong bias mismatch, particularly with linear models. Okay. So that being said, with that much warning on linear models, let's first step back and see what it looks like to interpret a linear model. So here is a linear model where we have just a partial dependence plot, okay? And this is just sklearn linear regression. And on the x-axis, we have an arbitrary feature, and then the output is the y-axis. And what you can see here is when we use the Shapley values, and the SHAP package in particular, to explain a linear regression model, there's actually a very direct correspondence between a partial dependence plot and the actual SHAP values you're going to get. Okay, so if xi is a particular feature's input value for the sample I, and phi I is the credit given to that feature for the model. And you can see it exactly equals the difference between this gray line, which happens to be the average impact of this feature, and the partial dependence plot. So we can actually write that out. The SHAP value for a linear model is literally just the coefficient times the feature's value mean centered. Okay, so if ever you're thinking, how do I think about these values? What is their intuitive meaning? I think it's often helpful to go back and look at what this does in a linear model. Realize it's just the coefficient times the mean centered value. It turns out the exact same thing happens for a generalized additive model. So here we just have an XGBoost with max step 1, which means that there's not going to be any interaction effects between your features. And now again, we see the partial dependence plot. We plot the expected effect of this feature according to the partial dependence plot, and then we just draw a line between that expected mean value and the partial dependence plot, and it equals exactly the SHAP values. Okay, so we can write that out again. It's just the features, the additive effect of that feature minus the expected additive effect of that feature. That's the SHAP value for a GAM model. What this means is that if you use these types of black box explanation methods like SHAP or on simple models, you will get lossless explanations. And by lossless, I mean, if you were to plot them, you will get the same partial dependence plot, you will perfectly recover the shape of the underlying model. But what happens when you have more complicated models? Well, when you have more complicated models, there's going to be nonlinear interaction effects. And that's when the sort of the axiomatic fairness principles really kick in and force you to share credit for these interaction effects in sort of a fair way among the input features. And when you do that, you're actually going to cause vertical dispersion in the scatter plot when I plot the importance of a single feature over many data points. Okay, so whenever you see vertical dispersion in your plot, that's a reflection of interaction effects present in your model. It's also an excellent way to quantify how much is being hidden by your explanation, right? Because it's often useful to understand what is your explanation error, right? An explanation, for example, a Shapley value explanation, is constrained to be a vector of numbers that tells you the importance of each feature. By definition, that has a fixed complexity and hence can't represent arbitrarily complex relationships. As your machine learning model becomes more and more and more complex, even though that's simply representing a single prediction, it's still not going to be able to perfectly capture everything that's happening in your model. Otherwise, you just have to look at the full model to get that. So you have this question, how much is being hidden by my explanation? How much am I sort of sweeping under the rug? And the answer is, you can quantify that in many ways by simply looking at a scatter plot of a feature and looking at its vertical dispersion. If you get tons and tons of vertical dispersion, then you know that almost all these effects are driven by interaction effects, and hence you're hiding a lot of detail about the model. If, however, you get a perfect line, like you would for an additive model, then you know nothing is being hidden, and your explanation is, in some sense, lossless. Now I'm going to skip back there. So I'm skipping through a variety of practical layouts of what matters here in different scenarios. So I want to skip next to the dangers of global importance feature measures. Okay, so we talked about how it's easy to just take the sum or the absolute value of a column to get a measure of global feature importance. But here I'm going to talk about how that's helpful, but also how it can hide things. So this is a mortality risk model. This is a real data set that was based off 20,000 people and 20 years of mortality follow-up. So it's a very detailed model based on all the types of things you get measured at a typical doctor's visit. And you can ask, what is the #1 risk factor for your mortality? And sometimes it's useful to let people think about that for a moment and then tell them, well, of course, it's their age, right? So being old is the #1 risk for mortality in the next 20 years. And that's not surprising, right? So that shows up at the top of our global feature importance plot. After that, it turns out that being a guy is the most risky thing you can do. And from there, we can, again, enumerate these types of risks. Okay, these are things that the model found very predictive of the chance of mortality in the next 2 decades of your life. So there's tons and tons of these, right? And we can only show 20 on the screen, but there's hundreds in this model potentially. There's a problem when we just make these types of bar plots. And that is, it conflates the prevalence of an effect with the magnitude of effect. Okay, so if you're looking at age, that is indeed extremely important, and it affects everyone, hence it shows up at the top. But we've conflated that with the magnitude of the effect, where the magnitude is potentially large, but what if it's large for only a small number of people? So to see that, that's another place where I think it's useful to use these sort of local explanations. In other words, this separate matrix, the same shape as our data set, to get better insights. So to do that, let's plot the Shapley value on the x-axis for each feature. And then we're just going to do a B-swarm plot, which is kind of like a violin plot with dots. And we'll do that for, let's start at the bottom with blood protein. And you can see that blood protein here has a long tail of dots stretching off to the right. What those are rare high magnitude effects. So if you look at the dot on the far right there, for that person, blood protein is potentially the most important feature for their mortality risk overall of everything. But you'll notice blood protein looks like it's not important at all in the global ranking. And this highlights a common pattern across lots of these features, particularly in this mortality model. It turns out that there's lots of ways to die young, right? Be wildly out of range in any of these things, and it's going to significantly impact your mortality. But that doesn't mean that you're going to see that in the global feature importance plot. Conversely, in case you're interested in Googling around online, there's no long tail stretching off to the left. In other words, there's no shockingly out of range you can be, and you will live another 30 years. But what we can see on the right-hand side here is by plotting all of the local explanations, we're able to alleviate some of the concerns that can come from just the global summary. Because remember, whenever you're taking an explanation, you're choosing what information to discard and what information to keep. So as you provide more and more detail, you're going to be able to see more and more richness in your data. Okay, so a bar plot is a great way to summarize things, of course, but if you want to get more insight into your data, it's helpful to have an entire matrix of local explanations that you can plot in rich ways like this. But of course, if you want to dig into it, you also want to understand maybe a particular feature. We can dig into this just like a partial dependence plot would. But of course, remember, since we have interaction effects in this model, since this is an XGBoost model, we're going to get vertical dispersion. And that vertical dispersion contains information. And so if you were to color, for example, by age, you'll see that this vertical dispersion is driven by an interaction effect with age. So systolic blood pressure is on the x-axis. The impact systolic blood pressure has on the model is on the y-axis. And this vertical dispersion is driven by interaction effects. We color by age, and we see essentially that early onset high blood pressure is more dangerous. And you'll find again and again, interaction effects are particularly informative in these types of models. In fact, we can pull them out directly by computing their interaction values and plotting them over, over time. But here's the interaction effect between male and female and age over a lifetime, and you can see the varying risks between men and women swap back and forth, peaking at age 60. So this is very interesting stuff that you would not see from a traditional plot if you did not pull out the interactions. So that's the value of dealing with the whole matrix, but it's also important to realize when you're making these explanations, you're not always trying to just explain the model's output. Sometimes it's useful to explain the model's loss as well. Okay, so here's an example where instead of explaining the output of the model, we're going to explain the loss of the model, and we're going to use it for model monitoring. So here's a model that we trained on a time, on a data set in a hospital. We used 1 year for training, and then we used 3 years just for follow-up monitoring. And if we take the training performance time, you'll see instantly test performance degrades, not surprising. But then you don't really see any general trends during the test performance period, other than it just seems to go up and down, up and down. I don't see any like clear, it broke here type things. But it turns out we actually introduced a bug into the model. This has thousands of features, but we just totally destroyed a couple reasonably important features. And the overall noise of just the mean squared error of the model bouncing around, this is trying to predict the duration of surgeries, is just totally washed out the impact of that bug. But it turns out if you were to explain the loss of the model, then that essentially deconvolves this output error into all of the thousands of input features. And then you can look at each of the input features for strong signals. Turns out, is a patient in room 6 in the hospital? Well, this is where we actually introduced the bug. And of course, now you can see it very clearly because the y-axis is the impact on the model's error. And then suddenly this feature, when it's red, starts hurting the model's error at the end of 2014, where a model bug happened. Of course, that's something we introduced. We can find the same thing in the real data. So here's a transient EMR record that we never would have, recording error, that you wouldn't have seen otherwise. In the feature, are they under general anesthesia? Turns out it was broken at that point. Here's a trend over time where just procedure differences change. So often when people are monitoring data for inputs to their models over time, they're monitoring just summary statistics of the data. But what you really care about is the impact that those features are having on your model's performance. So why not explain that model's performance in terms of the features and then monitor that impact and not just the data itself? And you can get much more specific tests. Finally, and this actually gets to one of the questions I think that came earlier, I think it's important to realize you don't just have to explain model output, you can explain model loss. You can also, it turns out, explain fairness metrics. So fairness metrics are functions of models, which are functions of data. And you can essentially explain a fairness metric so that instead of getting a single number, so here's an example where we've trained a simulated model to predict something, and we then measure the demographic parity difference for women versus men. Okay, so in this case, we have a significant disparity between the outcomes that this model is predicting between these two groups. So this is a very classic, even has a lot of basis in legality for measuring fairness of a machine learning model. The question is then, what do you do once you have this? What do you do once you've measured a demographic parity and realized that it's not good? Well, you can apply mitigation measures. Okay, so FairLearn obviously has a lot of great stuff for that. But I think it's also useful to say, well, I want to understand what's driving it, right? In this particular case, this model is a simulated model and it only has 4 features in it: the job history, the reported income, the credit inquiries, and the late payments. In this case, I've actually gone in and intentionally corrupted the reported income for men versus women. Okay, so that is the feature that has got a misreporting. So I think it's an underreporting of income for women was intentionally inserted into the reported income feature. And then we retrained the model and we know what was driving the bias in the model. It was a problem with the reported income feature and the fact that it wasn't properly recording income for women. That's what's causing our bias. If we explain the model, we essentially get SHAP values, which are again in the units of the model's output. And now instead of slicing men and women on the model's output, we can slice the SHAP values, men and women, and take the difference, and we'll get the demographic parity difference for men versus women, now broken out by input features. And I would argue that often this is going to be much more informative for debugging and identifying where to go next for fairness, because now you know that it's not the job history, the credit inquiries, and the late payments that's causing the disparity, it's your reported income. So you could do some post hoc fix, but I argue it might be better to understand what's in your reported income was actually causing this disparity and whether it's something you can fix at the root cause. So with that, I'm going to see a little bit of code, but we do not have a lot of time. So this is a URL that you're free to type in if you like. It's tinyurl.com, KDD SHAP 2020. And it's just a notebook. It's got a lot of this type of stuff in it that you can walk through and play with this stuff on your own. So I am going to flip over to that myself and use probably another 5 minutes or 3 minutes for that. I was hoping to have 10, but I want to save some time for questions and also be able to wrap up on time. So what we have here is some plots here where essentially we train a linear model and we make a partial dependence plot and we see that it's linear. Okay, and this is on housing data, so standard Boston housing data prices. You can see a connection between SHAP values and how they perfectly match this partial dependence plot. It turns out that if you just run a simple scatter plot with SHAP, you will see exactly the partial dependence plot line traced out by the SHAP values, just showing again that equivalence we were talking about. There are lots of plots inside of SHAP, so you can do shap.plots.whatever, and you'll get lots of interesting things. This is a waterfall plot, which actually starts at the expected value and then slowly shows you how each of the features adds or subtracts until we get to the final model predicted output. So in this case, the predicted output is 16, the expected value is 22. How did we get there? Well, it's the number of rooms and like their ratio and their index from the roads all kind of pushed it negative. And we can do the exact same thing for an additive regression model. So this is actually the explainable boosting stuff that I think Rich will talk about next. And we can see again that if you apply SHAP to this, you're going to get exactly the same thing as the partial dependence plot with no vertical dispersion. You can run the same type of waterfall explanation. You can run those summary plots that we talked about to understand the different scatters. And then if we run an XGBoost model, which now has higher order interactions, we get the same sort of general trend, but we get vertical dispersion because of interaction effects. And then we can actually color those to identify that it's driven by tax in this case. The number of rooms based on your tax code actually has some interaction effect in this model. And then I'm just going to skim over so that you can see what's useful if you want to look through this on your own time. But I think it's important to realize that if you're explaining a classification model, the output, again, I'm trying to harp on this again and again. As you're doing explainability, it's important to think, what are the units of the output that I'm explaining? And is that the real output I care about? So here, if you were explaining a logistic regression model and you tried to explain the probabilities, you would see tons of vertical dispersion on your model. But if instead you were to explain the log odds, you will now get a perfect linear relationship. Okay, so what does this mean? This means that if you're asking the relationship between the inputs and a probability for a classifier, even if it's a linear classifier, that's not a linear relationship, and it's going to be complicated to explain that. But if you're willing to think about things in the log odd space, things become much more simple, okay? Same thing happens, again, for a lot of this stuff. Now, I'm gonna end here, but I wanna highlight just a few pieces here. So this is a clustering. Essentially, you can make a heat map of these things. So instances on the x-axis, features on the y-axis, do a clustering of these features, and you're gonna understand substructures in your data. So for example, capital gain here is driving the importance of this group of features here on the left, whereas capital loss is driving the gain of people on the right, and a variety of other features in the middle. And when you're doing scatter plots, you'll see separations, such as for people who are older, there seems to be this separate group down here. And if you start coloring by various other features, you realize those are the people with high capital gain. So for some reason, this model believes that people with high capital gain are going to behave very differently than other people during retirement years. So I think we're going to end right there. Oh no, I will do one more thing. And that is, I think it's important to point out that correlated features make a difference. Okay, and so I'll just point this out and say you should check out the notion of clustering your features by features that are very redundant with each other, and then potentially consider plotting those in a way that respects that clustering. So here's a bar plot where we have essentially clustered features by the redundancy and shown that relationship and marital status are actually almost perfectly redundant in this data set. This is just a standard census data set. We would never have noticed that it happened to be relationship that got all the credit, but that was entirely arbitrary, since it turns out they were almost entirely redundant. With that, I think I will stop there. And
That's
yes,
great,
I will
Scott.
resend the link. So
yeah, if you could resend the link, Scott, that would be great. And then there's time for you to take some questions.
Okay. I will send that quick link and URL. All right, let me scroll back up to the question. Okay, I'm gonna start at the one at 10:06 and then work down and see how far we can get through. So question, in lending, we're less concerned with the question of what attributes led to a certain score than we are of why this particular score was returned rather than another. They seem to address the former. Thoughts on how to address the latter? CFPB interpretation suggests a comparison of goods. Can that be done with Shap? Okay. So what you want to, let me rephrase that, make sure I interpreted it correctly. When you're in finance and you're providing an adverse action recommendation to a consumer, that's regulated by the CFPB in the US. And those adverse actions are designed to tell a person why they got a particular approval, for example, or decline. An adverse action is a decline, obviously. So what matters here is how you're going to compare a counterfactual, right? So you got this score and not that score is implicitly saying there's some other counterfactual that could have existed where you would have been approved, but you're not approved, okay? Now there are thousands or millions of potential configurations of inputs that would have led to an approval, and I could show you lots of them. But the way Shap addresses this is, I think, actually fairly consistent with the way the CFPB originally had guidance for linear models. And that is, you compare either to the training data saying, how does each feature compare to the typical customer? But I think it actually makes more sense, and this might be what you're alluding to compare it to people who are approved. And this is inside Shap where you can provide your background prior, your background data set. So like when you're doing an explainer, you give it the model and you give it data. And that data is used for the taking expectations. If you use that data as a way to set your prior, that's the right way to think about that. And I think that would make sense to set that prior either right at the boundary of people who get accepted or denied. So select a group of people who are right at the boundary. Then when you get positive values, you're gonna see this is why you're above the cutoff, and negative values, you're gonna see why you're below the cutoff. Or you could say, I'm going to use people who are just accepted. Both of those, I think, produce very semantically meaningful priors. And I think that's the key part here, is to think about what is the prior, what's the alternative that I am explaining with regard to. Hopefully that's helpful. Let's see. Next, seems unlikely to be in the situation though, if you knew the problem was nonlinear, you just avoid using a linear model anyway, or you'd likely start with an ensemble anyway. In other words, saying, if I knew the problem was nonlinear, I wouldn't be using a linear model anyway. I'm not sure. I think that's probably back to the comment about whether you should or shouldn't use a linear model. I would say a lot of people use linear models because they seek interpretability, even though they do not have good reason to believe that the underlying mechanism is linear. And that's the caution I was trying to provide. Is there heuristics to identify which features have interactions and should be looked at in detail? Yes. If you're able to explain it with Shap, I would plot the scatter plot for each feature and observe how much vertical dispersion is present. That will tell you how much interactions are present. If you would like to know more, you can run for an XGBoost model and compute the actual interaction values, which I didn't get into, but you can essentially predict the interaction contributions directly. For features that are highly correlated, Shap may pick one over the other as an explanation. In the example on mortality rate, there's a certain level of correlation between age and blood protein, but both global and local explanations of Shap indicate that age is the #1 factor for that person. But for a doctor, the high blood pressure may be a better reason code to be returned as an actual insight. So there's two things here that I think are useful very quickly. So the first is correlation matters a lot. And I'm sorry I didn't get time to touch on it much, but that's why we're actually releasing very soon some extensions that allow you to directly incorporate a clustering of your features into the model perturbation process. And that will allow you to visualize very quickly which features are redundant with each other, and hence the explanation, the dependence on those features should be viewed as a group. And now I would say this is not really an aspect of Shap as much as it is an aspect of the model, right? So the Shap's just telling you which feature the model depends on. The model itself, of course, could arbitrarily pick a feature. If you're interested only in features that are actionable, okay, so you're saying high blood protein is actionable, age, it turns out, is not actionable, that we know of. In that case, I think it's useful to use the background data set to pick a comparison group that's actually more useful for your person, right? So if you think that age is not something you want to be important, then when you're defining the background data set, you could actually define a custom background data set for each sample that is conditioned on the age. And in other words, you're choosing a background data set that is a cohort, essentially, you're comparing with that has the same age as you. So if you have a set of features that you can't change, then you could go off into your data set for each sample, find a group of people that has the same, similar values for those features, use that as your reference distribution, and then by definition, all the importance is going to be given to the actionable features in Shap, if that's helpful. What do you think, Rich? Maybe one more, two more? What do you think?
Sure, go for it.
Okay. Great. I'm interested in feature importance for model monitoring and detecting feature drift. We could see lots of noise in a given feature due to interaction effects. Do you have recommendations for how to minimize FP in this case? So unfortunately, I don't remember what FP is. Lots of noise due to feature interaction effects. So I think if you're interested in monitoring over time based on Shap attribution values, and you're seeing a lot of effects, a lot of vertical dispersion due to interaction effects, and that's making it hard to debug what's going on in the model, like what's actually due to that feature, it is possible to compute mean effects, main effects, and that could be useful, which is equivalent to essentially computing a partial dependence plot for Shap. The other alternative is if you're using XGBoost, you can compute the interaction values directly, and that will essentially further decompose your output into a matrix instead of a vector, and that will give you more and more data streams to monitor. Obviously, you have to watch for p-value effects and things like that to make sure you're not looking, when you're monitoring 1,000 streams at the same time, you want to set your thresholds accordingly. But that's the first thing that comes to mind. I'm not sure if I'm answering that directly. And then I'm going to do one more, and then I'm going to ask maybe that these get, if you guys have more settings, maybe how would I best do this? If people want to ask more questions, how about you just post them as GitHub issues and I will go through them this afternoon. So we'll go from there. If I didn't get to your question there, I apologize. Does this link work for everyone? Can SHAP be applied in sorry, question. Can you clarify how SHAP values deals with collinear input features and how does SHAP and Lime compare? So SHAP deals with collinear input features in the sense it doesn't matter. If you use the original SHAP, it's going to perturb the features independently, and the collinearity is going to primarily affect what the model does, not how SHAP deals with it. That being said, often there are times when you're perturbing the inputs to a model, you don't want to know how the model depends on a broken correlation between two features, right? So sometimes it does not make sense to perturb features independently. And if that's the case, there is actually a way to provide a hierarchical clustering of your input features to SHAP, and it will respect that during the perturbation process so that it will only perturb features according to that group, that hierarchical grouping. And that means you can always view that cluster as a cluster and know that there was no sort of unrealistic perturbations driving your explanations. I'm going to cut it off there. But again, I'll be happy to look through things later today if there's other questions that I didn't get to. I don't want to run into Rich's time more than I already have.
Thank you, Scott. That was great. So, okay, so I'm going to switch gears now. Share my screen. And hopefully everybody can see this and see it in presenter mode.
I can.
Okay, great. So I'm going to talk about EBMs, explainable boosting machines. Number of people have worked on this project, including a few people who are here giving part of the tutorial. So let's just jump in at the high level here. So black box explanation is mainly what we've been talking about so far. When would you use black box explanation? Things like Lime, SHAP, partial dependence. Well, if you don't have access to the data, or the model was pre-trained and just given to you, or a specific model type is required, like a neural net or a boosted tree, things that we consider black box models, or you're trying to understand a complex pipeline from beginning to end, and you need to treat that pipeline as a black box, then you really have to use the kind of black box explanation methods that we've been talking about, such as Lime and SHAP. But there are other settings where you can use glass box methods. So maybe you have access to the training data and you're the one who's going to be training the model. And maybe you're the one who ultimately has to debug the model, retrain the model, improve the model accuracy month after month. Then you probably should use glass box machine learning methods such as EBMs if they're appropriate for your data set. And the advantages you get using glass box methods is that the intelligibility is now exact. You really understand exactly how the model works. It's not approximate as some of the black box explanation methods are. And this improved intelligibility can lead to faster debugging and model improvement. Now, you've already seen this in Marco's presentation. Maybe there's a trade-off though between accuracy and intelligibility. So the more accurate models like boosted trees and neural nets and random forests aren't so intelligible. And yeah, you'd like to use these intelligible things over here, but they're just not accurate enough. Truth is that's just often not true. So it turns out that if you're doing tabular data, so by the way, this is true if you're doing pictures, acoustic, and large text data sets. So those are places where deep learning now is king of the hill. And you definitely have to use deep learning methods to do state-of-the-art accuracy on those problems. But if you're working with tabular data sets, usually this trade-off is not true. And these EBM methods, these explainable boosting machines that we're going to talk about, in practice, they have just as much accuracy as boosted trees, random forests, and neural nets. And they have even more interpretability than these linear methods, in part for the reason Scott was talking about, that using a linear model, using a model that's too simple can actually hurt intelligibility. So these models are sort of as complex as they can be and still remain interpretable. And then that helps because of the kind of things Scott talked about. So just some examples. So here's a study on a number of data sets, and EBMs, if you look at the average score down here, 0.866, that ties with the full complexity models such as XGBoost. Here's another study from another paper, and we've used arrows to show you where the EBMs fall. And I think you'll see this is a paper by Cynthia Rudin et al. Doing work on recidivism prediction for 6-month recidivism and 2-year recidivism. And their finding is basically that the interpretable model, the EBM, is performing approximately as well as more complex models such as XGBoost. And yet here's another paper from Hinton's group at Toronto, and they're also finding that EBMs are doing quite well compared to other more complex models. So it's kind of true that these models aren't going to lose you much accuracy. So the question is, how is that even possible? Well, let me give you an example of this. So this is a function space. Here's linear models, a weight times a feature plus a weight times a feature plus a weight times a feature. Those are simple models, easy to understand, but very low complexity, not going to be powerful enough for many data sets. Here's full complexity models at the bottom, an arbitrary function of all available features. Unfortunately, this arbitrary function will often not be interpretable. There is something in between, and that's the space of additive models. So here we have a function of a single feature plus another function of another feature plus another function of another feature. So we have functions of individual features. The functions can be arbitrarily complex, but they can only be functions of one feature at a time. And that's a tremendous restriction on this model class. We can make that model class a little more powerful. So here's a sum of all functions of individual features. That's this sum just written out in summation notation. Here's a sum of functions of pairs of features. So this can now do pairwise interactions, and we can go further if we want and include 3-way interactions, but we're actually going to restrict ourselves to main effects, functions of individual features, and a small number of the most important pairwise interactions because this remains intelligible. And then the remarkable thing is if your algorithm is good, you'll get very high accuracy out of this on most tabular data sets with no loss in accuracy compared to other methods. Now, we didn't invent these. Generalized additive models were invented by Trevor Hastie and Rob Tibshirani at Stanford in the late 80s. But they were very conservative when they fit these models. And although they were popular for a while in the 90s, they got less attention perhaps than they deserved. And our contribution is to sort of modernize these things by putting them on modern machine learning steroids. And in the process of doing that, we get high accuracy out of them, even improved intelligibility, and it turns out you can even edit the model. And now we've released an open source package to make it easy for everybody to use these things. So here's a sketch of the algorithm. So we've got a number of features, features 1 through n, and we're going to go through a lot of iterations, maybe 5,000 or 10,000 iterations. So we go to feature 1 and we grow a very small tree. Maybe it only has 2 or 3 or 4 leaf nodes, and it can only use feature 1. And we use a very low learning rate. So this hasn't learned very much yet. And we update the residual compared to the targets. And then we go to feature 2. And when we go to feature 2, we grow a very small tree on the residual that can only use feature 2. We update the residual, we go to feature 3, feature 4, and we keep growing tiny trees that can only look at one feature at a time. In the end, we've gone through all of the features in some random order maybe, and we've now got a model that's seen every feature once, but the learning rate is so low that it hasn't learned very much yet. So now we come back, we go to feature 1, and we grow a second tree on feature 1. So this is a boosting algorithm under the hood. So this tree gets added to all the trees that already exist in the model from iteration 1. We update the residual, we grow another small tree for feature 2. Round robin fashion, we go back through all the features again. So now we have 2 trees for each of the features. Then we do another iteration, we add another tree for every feature, another iteration. Eventually we do maybe 10,000 iterations. And we might use early stopping and find out that, iteration 5,000 was better than going all the way to 10,000 because 10,000 was overfitting. So that's kind of normal. Here's the interesting thing. We now have, say, up to 10,000 trees, which are all trained only on feature 1. We can summarize those trees as a graph. That is, we ask all these trees, what do you all predict on average for, say, age 18, for age 19, for age 20, for age 21, age 22? We can summarize the prediction of all of those trees as a graph. Once we create the graph, we can throw away the trees because they're not needed anymore. We have a perfect summary in the graph. This graph is now a representation of the function that the model has learned for feature 1 and its contribution to some score or risk. We can do the same thing now for feature 2, summarize all those trees as a graph, throw away those trees, go to the remaining feature columns, and now what we have is a graph for every one of these features, and we ultimately throw away all the trees. We train millions of trees, but we don't need to keep them in the end because the graphs are a perfect summary of all of these things. And the beautiful thing is that because each graph is a function of only one feature, we can now understand exactly how the model works by looking at the graphs. Okay, so now what I'm going to do is I'm going to jump into using EBMs on a number of case studies, and this will sort of explain some of the value of this sort of method. And then we'll wrap at the end and take questions. And I don't know if I'll get through all of these. I'll just stop when I have to. Okay, so you may have seen this pneumonia mortality example before. Let me run through that because it'll help you understand the model better. I'm going to go a little slower in this. We have a pneumonia data set from a long time ago. There's 46 features in it. We know things like the patient's age and if they have cancer or asthma. We know their heart rate, their body temperature. We have a blood test result, so we know the pH of their blood, the glucose level of their blood. And a doctor has taken notes on a chest x-ray. So we have findings from the chest x-ray. So we have 46 features. Now remember, the model is a function of a feature plus a function of a feature. So we're going to end up with 46 graphs. 46 columns in that previous slide of how the algorithm works. So those graphs might look like this. Here's a graph of risk as a function of age, risk as a function of asthma, glucose, blood urea, nitrogen. And the way that works is you find the patient's age, maybe they're age 50, you read off the Y value, and then you write down the Y value. You find out if the patient has asthma, then you write down the Y value. Find if the patient's respiration rate is high or low, write down the Y value. These Y values are log odds. So basically a +1 more than doubles your risk, and a -1 cuts your risk in half. So we can take the sum of all of these things, which gives us a score. The higher that score, the higher the risk, lower the score, the lower the risk. And we can convert this to, in this case, it's a probability estimate that the patient might die from their pneumonia by just doing the standard logistic correction, which is 1/1 plus e to the minus score, sum of all these numbers. Okay, and if this had been a linear model, a logistic regression model, for example, this would just be a linear model sitting up here where the score is. But instead, we have a more complex model that was learned by learning all of these feature graphs in parallel by going in round robin fashion through all of them. Now, once we have this probability of death, you know, the score basically tells us how high or bad this is going to be, but in a as Scott said, it does it in a nonlinear way. So a score of 5 is very high risk. A score of 6 is much higher risk, but 5 is already like 99% probability of death, and 6 is like 99.5% probability of death. So we take the score, and then we pass it through the logistic function, and then that gives us the probability of death. So if adding up all these numbers gives us a -0.78, then the probability of death in this case would be about 30%, which is actually very high. You want to be a sum of scores here of about -2 or -3 to have low risk. Okay, so that's a big picture of how the model works, but let's look in detail at some of these graphs now. This is what the model learns for risk as a function of age for your chance of dying from pneumonia. And the bottom is just a histogram. Most of our patients are between 60 and 90. And this is what the model has learned. This is the summary of those thousands of trees that were all able to look at the age feature. And remember, to use this model, you have to look not only at this graph, but you have to look at all the graphs together because they all add or subtract from your risk, exactly like Scott was showing in these waterfall plots. Okay, so it's good to be young. Young is, the model says anybody under 50 looks like they're low risk with respect to age. And the model could have distinguished between people in their 20s, 30s, and 40s, but it didn't see any statistical evidence to do that, so it didn't do it. Risk goes up slowly as you go through your 50s into your 60s. Risk rises pretty rapidly, right around 67, 68, 69. It turns out that's a retirement effect. We see this in many medical data sets where retirement you might have thought would be good for you, but in practice it can actually be harmful to you for a number of reasons. I mean, maybe your insurance provider has changed. You're now on Medicare perhaps. Maybe you've moved to your retirement home. Your daily activity level has changed. Your urgency to get care has changed. Maybe you don't even have a doctor after you've moved yet. So for lots of reasons, you might not get to care as quickly, and that seems to cause a increase in risk. Then risk goes up pretty rapidly through your 70s and your 80s as you get elderly. I think that's to be expected. Surprising step function in risk right at 85. We're pretty sure, doctors and insurance companies tell us there's no reason why they would treat an 87-year-old differently than an 83-year-old. And we're pretty sure that what's happening here is basically, you're on the elderly side of elderly if you're over 85, especially from a data set that's back from 1989. So you're considered extra elderly if you're over 85. And this is a round number, and doctors use round numbers when making treatment decisions. And we think what's happening is basically doctors are saying something like, well, you know, grandpa's 87 years old. Grandpa has a number of illnesses associated with being so elderly. That's why grandpa's got pneumonia now. The first round of antibiotics didn't help. Maybe we're not doing grandpa any favors, and maybe it's time to let grandpa pass. Maybe we shouldn't continue to fight too hard. And back then, pneumonia was sometimes called the old man's best friend. This idea that it might have been a friendlier way to pass away from pneumonia than from the sort of illnesses associated with being so elderly that caused you to get pneumonia in the first place, these long wasting illnesses. So anyway, we believe this jump in risk that's right happening at 85 is because of a social effect. Basically that we've decided to treat patients who are over 85 a little less aggressively than patients who are under 85. Now there's an interesting thing happening at another very round number, right at 100, 101. Risk is coming down. And we think this is the opposite of what's happening at 85. It's another social effect. But basically, we think when a patient has made it to being 100 plus, when they've made it to being a centenarian, and you have a treatable illness such as pneumonia, we think basically doctors just don't give up on the patient. It could be the patient doesn't want you to give up. It could be the patient's family doesn't want you to give up. And it's easily the case that the doctor doesn't want to give up. And when I give this kind of presentation to medical audiences, invariably doctors come up to me afterwards and tell me this is exactly what they see, which is that when they have a patient who's made it to some magic age like 100, they just don't want to give up if they think the patient is treatable and that the treatment might help. So we see a reduction in risk here. Now, a very interesting thing, the model has 46 graphs. I can't show you all of them. And then 10 graphs for pairwise interactions. I'll show you one of those. We've really been able to understand in a nuanced way what the model has learned about risk as a function of pneumonia. Being under 50 is okay, not too bad to be 60. Retirement's not good for you. Over 85 is higher risk than under 85. Over 100, you get extra aggressive treatment. At least that's our interpretation of the model. This model, it turns out, is the most accurate model anyone can train on this data set. So it's more accurate than neural nets, boosted trees, random forests. It's a very, very accurate model. And yet we understand all of this detail, which is great. Now, here's an interesting question. The model, it turns out, because it is represented as a series of graphs, is also editable. That is, we can change the model. If we redraw the graph, the model will do what we say. So how many of you think that it's true that a patient who's 105 is intrinsically lower risk than a patient who's 95, which is what the model has learned? So if we need to, we can talk to a doctor, figure out that the model's really not quite right here, and we can edit the model. Now, we've got to be careful. We're overruling the statistics in the data when we do this. But in the process, we'll probably have a model that's safer to release in the wild, because we wouldn't want a model to go out and say that 105-year-old patients are lower risk than 95-year-old patients, because we don't actually believe that. It's interesting, though, the model probably is correct if your interest is actuarial. That is, you're interested in just knowing as an insurance company whether the patients are likely to survive or not, so you know whether to charge them more for their insurance or to keep money in the bank for their insurance. So you sometimes want to edit the model and sometimes you don't. So that's a very important lesson, which is that the correctness and accuracy of a model depends very much on how it will be used. And Marco emphasized this in his first presentation this morning. So you really need to know how the model is going to be used in order to be able to interpret what the model is doing and whether it's right or wrong. Let me show you some things this model learned about pneumonia. First of all, jumps at round numbers, things like 67, 68, 85, 100, they're almost always due to human effects. There aren't that many phase changes that happen in the real world in biology. The model learned that asthma is good for you. That is, having asthma is lower risk than not having asthma. That's weird, right? Why would having asthma be good for you if you've got pneumonia? The model learned that having chest pain and heart disease is also good for you if you've got pneumonia, right? And that doesn't make sense either. And it turns out the model learned that having an obstructed lungway, which doctors recognize by the way you breathe, you're wheezing, it's kind of wheezing called stridor, that's also good for you. So now none of this makes sense, right? That having asthma, heart disease, chest pain, and stridor is good for you. Why is the model learning this? It turns out they're all true statistics in the data. And the model is learning these things because the asthmatics notice the symptoms of pneumonia early. They try their inhaler, it doesn't work. They call their doctor. The doctor says, oh, the inhaler didn't work, get in here. And then the doctor considers the asthmatic to be high risk, so they get treatment earlier than normal patients. And if you've got a treatable illness like pneumonia, early treatment is good. Same thing with chest pain. These patients think they might be having a heart attack when they start coming down with pneumonia. So they get to the ER very quickly. They get to the front of the line of the ER. They know they're not having a heart attack within a minute or two now with modern technology. And then later in the day, they realize, oh, you've got pneumonia. And again, because they have a history of heart disease, they get very high quality treatment. Similarly, stridor is so bad that these patients sound so terrible, they're forced to go to the hospital, either by themselves or by anybody who's around them says, you sound terrible, you need to go to the hospital. So all of these conditions are things which cause patients to get to the hospital faster than patients who didn't have these conditions. And although doctors will tell us these conditions are actually harmful for you if you've got pneumonia, in the net, they turn out to be advantageous only because they got you to care very, very quickly. So we would want to redraw this graph for asthma, for example, to make it a flat line so that there was no improvement in risk with having asthma, or maybe even make risk go up to plus 0.4 or 0.5 if a doctor said, I want the asthmatics to be higher risk. So we would be able to edit the model. There's something, though, that's even worse going on here. It's an additive model, so all these effects contribute to each other, add. So think about it, a patient who's 105, who has a history of asthma, a history of heart disease, and who now has an obstructed lungway is considered to be extremely low risk because all of these things lower the risk. And nothing could be further from the truth. But the model is rewarded with high accuracy on the test set for doing these predictions. And that's because the test set is a random sample of the training set. It has exactly the same statistics as the training set. And it turns out all of these things are statistically true in the data, though inappropriate to use for healthcare. So it turns out the model is rewarded with extra high accuracy for actually predicting these very wrong things. So one thing, you might think you could fix these problems by removing features like asthma, heart disease, chest pain from the model. Turns out that doesn't work. One, you have to keep some of these features in the model. Features are important. And the bias in the model is coming from the outputs, from the targets, the statistics of who lives and dies, not from the input features. And it turns out if you delete some of these features because of correlation of, say, asthma with other features in the data set, it'll still try to learn that asthmatics are lower risk using these correlated features that Scott was talking about in his presentation. So it turns out now you have to take these offending features, and if you're going to train a glass box model like an EBM, you actually intentionally put offending features in, like you might put in race or gender and things that you would think would be terrible things to add to a model that would lead it to be biased. Now you should put them into the model, let the model be as biased as it can be. You'll see now the bias that's in the training signals, and then you can go to those graphs and you can surgically remove the bias by flattening the graphs or offsetting the bias. So it's a completely different way of dealing with bias. Now, intelligibility is useful not to just correct the model, but you might be able to learn from the model. So this is the blood urea nitrogen. Again, this is pneumonia. And doctors really like this graph. So this is a blood test, by the way, all of you have had. Whenever you have a blood test, this is measured. And basically it shows that risk is getting high by the time you get to about 35, flattens off at 50, it peaks at around 100, and then drops and stays high. Why did doctors like this graph? They saw treatment effects in the graph. That is, doctors start to treat patients at about 50, a round number. The doctors use round numbers all the time when deciding treatments. And notice the risk goes flat just above 50. And that's not because 60 is better than 50 or no worse. It's because the treatment is effective. There's also a treatment effect here. At 100, doctors start to give patients dialysis. 100 is another very round number. And what happens is dialysis, if most of the patients are getting dialysis, say by the time they have a blend of 110 or 115, their risk is actually lower than patients who are, say, at 90 or 95 who might not have gotten dialysis. So one of the things we can do is we can play a game. Like doctors said, man, risk is already pretty high at 35. Maybe we should start treating at 35 and not wait till 50. And this curve would flatten off even earlier. Especially this curve. It's really unfortunate that patients at 115 are lower risk than patients at 90, since dialysis is a reasonably safe treatment. So we can play the what if game because it's an additive model, treat it like a spreadsheet. And we can imagine that if we started to give treatment, say at 85 or 90, then the risk curve conservatively would look like this diagonal line here, this red line. It probably would go down even lower, and then it would have to join up somewhere around over here. So this is a conservative estimate of what it would mean to place the treatment at 85 or 90. And by looking at the difference between the red line and the green line that was learned from the data, this is people who are dying. This is probability of death. And by looking at the number of patients who fall into this region, it turns out we can estimate that in the US alone, by changing this one treatment threshold for just one condition, which is pneumonia, we can save 2,500 or more lives a year just in the United States. So it's remarkable when you can learn this sort of thing just by training an interpretable model, a really high accuracy, high fidelity interpretable model on your data, and then having human experts look at the model and see what they can learn from it. There are treatment effects, by the way, all over in your data. This is systolic blood pressure. This is normal blood pressure where it's low. Notice there's a rise right around 150, and then patients start to get treated, and the treatment actually is so effective, risk comes down a little bit, just like we saw for BUN. And then notice these peaks and drops, peaks and drops, peaks and drops. This is not a true risk profile, for systolic blood pressure. This is because treatments are kicking in at 175, at around 200, and around 225. So treatment effects happen all the time in data. It's not just in medical data, by the way. They happen all the time in any sort of economic data because we're often making decisions about what to give or not give the customer. Let me show you an interaction, and then we'll be done with pneumonia. So this is risk as a function of age. You already saw this graph. This is risk as a function of cancer. As you might imagine, having cancer adds to your risk. But just like parity, exclusive or, there are some things that can't be modeled as a sum of risk of age alone plus another term, which is risk of cancer alone. You really need to model both of these things together. And as Scott said, this is where you would see vertical dispersion in the Shapley plot because there's an interaction between these variables, and you can't model it like the Shapley plot for age will show vertical dispersion and the Shapley plot for cancer will show vertical dispersion. So let me show you what the interaction looks like. So this is age now on the x-axis, age on the y-axis and cancer on the x-axis. And we're using a heat map now because it's a 3D plot. Draw your attention to this yellow, which is high risk. This is adding 0.5 to patient's risk if you're down in this lower right-hand corner. This is very young patients who have cancer. Why would being a young patient who has cancer be extra high risk? It doesn't seem sensible. We looked into it, and it turns out this is patients who had cancer as teenagers. They had cancer that was very aggressively treated because we treat adolescent and teenage cancer very, very aggressively, more aggressively than adult cancer. And their immune systems have been knocked out, and they still have cancer, or else they wouldn't be labeled as having cancer in our data set. It had to be 18 to be in our data set. So that's where our data starts. So these are very young patients, very aggressively treated for their cancer because they were young. And then it turns out we've knocked out their immune system. And because of that, their pneumonia is now extra high risk because if your immune system isn't functioning properly because of the cancer treatment and you've now got pneumonia, you're at extraordinarily increased risk. And that's what the model is figuring out, is that there's a special group of very young patients, it's a very sad story, special group of very young patients who have been treated so aggressively with chemotherapy that the pneumonia is now extra high risk for them. And the model has learned this. Okay, we're going to go through these other case studies much more quickly, and then we'll wrap up. So this is ICU mortality, chance of dying if you're in the ICU. This is PF ratio, how well you're breathing, how well are you converting oxygen in the air to oxygen in your bloodstream. A low PF ratio is bad. This means you're not breathing well. High PF ratio, most of us are out here and are healthy. There's an interesting little detail. What is going on right here? Why at a PF ratio around 300-400, why is risk suddenly going down and then going back up? What's going on? So we talked to doctors and we thought, oh, maybe it's a round number, because we see lots of round number effects, like that drop that we see in risk at 100 or something like that. Doctors say, no, this is not a round number. It's 323.6. So that's not a round number. Maybe it was a round number in metric units and the data was converted to English units. No, that's not the case. These are the natural units. So we started doing detective work. We asked what was the mean of the PF ratio feature. Turns out the mean of the PF ratio feature falls exactly here. So we're seeing a weird disturbance in what the model learns right where the mean of the feature is. If you know about machine learning and missing values, there's a good chance that the missing values were imputed with the mean. And that's exactly what happened. So notice that the risk here is as low as the risk for the healthy people. Missing in medical data often means you were healthy with respect to this feature, so they didn't even bother to measure it. So that's why it's missing. It turns out 60% of our patients, they didn't bother to measure the PF ratio because it's not that easy of a measurement to make. So it turns out we have a lot of healthy patients sitting here at 323 in this bin, and the model has correctly learned for the risk to be low for these patients. Now you might think, oh, well, that's okay. Let's let the model do that. Those are all missing value patients. Some patients have a real PF ratio of 323 and would fall in this bin, and their risk should be up here. They're higher risk. So when you see this sort of thing, you want to immediately do detective work, figure out what's going on, and then we immediately stopped imputing missing values with the mean in this data set. In fact, we hadn't done it. Somebody before us had done it before they got the data to us. So we immediately recognized a problem in the way the data was pre-processed, and then we went back and we started seeing these little bumps on a number of graphs. So it turns out we completely changed how we pre-processed the data based on this little blip that we saw in one of the graphs. So here's the German credit data set you might have heard, the lending data set. So this is months of the loan duration, and credit risk goes up. And the difference between minus 0.5 and plus 0.5 is pretty big. That's an increase in odds ratio of E to the 1. So that's a 2 to 3 increase in odds ratio between being a very short loan and a long loan. So this is interesting that the model has learned this. It wouldn't necessarily be the case for all loans that increased loan duration makes them higher risk, but in this data set it did. This is interesting. So this data set is used a lot for bias and fairness work, and that's because the data set includes foreigners versus native Germans. And the model predicts low risk for the native Germans and high risk for the foreigners. So that's why it's an interesting data set for looking at bias. Are foreigners treated differently when they're given loans? What's interesting, though, is here's the first sign that there's a problem. Notice that the error bar is very small here for the foreign workers, and yet it's modestly big for the German workers. We looked into it, and it turns out 98% of the people in the data set are foreigners, and only 2% are native Germans. So that's interesting, right? It tells us there's very few of these, lots of these. There's a good chance the data set was never intended to have any native Germans at all, and a few of them just sort of leaked in by accident. And it was always intended to be a foreign data set, which right away, makes you question whether you should use it for looking at bias. So these very unequal error bars were like our first sign here, not the height of the graph, but just the size of the error bars were our first sign that there was a problem here. Then we started looking more at the model. Here's another striking feature. It turns out this is the loan amount in Deutschmarks. And this is 4,000 Deutschmarks. And notice that risk is pretty low down here and then goes up rapidly, a step function rise right at a round number at 4,000. So I started looking around, trying to find out why would 4,000 Deutschmarks be a magic number in German lending, because it's not that much money. This is an older data set, by the way. And it turns out at the time of German reunification, when East Germany is joining West Germany, they allowed East German Deutschmarks, which were not very valuable, to be converted to West German Deutschmarks 2-to-1 for any amount under 4,000 Deutschmarks. And they're basically being nice to the East Germans and basically saying, we're going to give you a little more value than your money is actually worth, just to sort of help you join our economy. But once you get over 4,000, then we're just going to convert that 1-to-1 to Deutschmarks. Very, very interesting. So now we know, because of this little rise and the detective work that it led to, looking for 4,000 Deutschmarks, we now know this is a data set that's been collected at the time of German reunification. The data set was really probably aimed to only look at foreigners, that is East Germans who are joining the West German economy. And that what's probably happening here is that some people are taking out loans in order to get more than 4,000 Deutschmarks so that they can get a conversion here. And those loans under 4,000 are safe, but they start to be less safe over 4,000. So basically, by looking at the graphs and doing some simple detective work, we were able to figure out what this data set is about. And it sort of tells us that this data set probably should not be used for any future research in fairness, bias, or transparency. And that's because the data set really was aimed specifically at East German workers who were entering the West German economy, not a situation where you can really detect bias between West German and East German. Let me tell you a little bit about some work we've done with Wikipedia malicious edits. So about 160,000 edits per day on Wikipedia, right? A lot of people use it. About 10% of those edits get flagged as being damaging. That is, they were malicious. The person was not trying to improve the page. They're trying to hurt the page by adding something like a curse or who knows what. And this is just looking at one of the features to try to predict maliciousness. And the vertical scale here is probably log odds of being malicious. So, +1 is double the log odds, +2 is 2 times the log odds. So this person has 5 times the probability of doing a malicious edit compared to this person. So what's the horizontal axis? It's seconds since the person registered to be a reviewer, an editor at Wikipedia. And this is on a log scale. So this is, 2 to the 2 seconds, 2 to the 4, 2 to the 16, 18 seconds, right? So this is the log scale. Let me just show you some of these things. So remember, up is higher risk, down is lower risk. This little bump that the model learned is right at 9 months. Kind of interesting that there's a bump at 9 months. This little bump, big bump, is right at 1 month. Why is there a bump at 1 month? It turns out your password, if you were logged into the system, expires after a month and you have to re-log in. Your password doesn't expire, but your login expires and you have to remember your password. And a lot of people who are doing malicious edits were never serious enough that they actually remember what their password is, so they can't log in again as that editor. This is 5 days. This is 30 minutes. This is 60 seconds. That's 30 seconds, that little tiny bump. And then that's 5 seconds. So notice that all the bumps that are happening in this graph are happening at sort of round number units of time. This little tiny one at 9 months is interesting. We're pretty sure that this effect is actually students who are in class, imagine before COVID-19 when we were actually in class at school, who have basically, they're bored and they've logged into Wikipedia to do some malicious edits. And they do that for a year, but next time after the end of the semester, the summer is sort of, they come back the next year and they don't continue doing it, or at least they don't do it with the same account. So the model seems to have detected something which, this is not pregnancy, this is something to do with the school year and student behavior. But now let's talk a little bit about pregnancy. This is what's known as maternal morbidity. This is that something bad is going to happen to the mother during labor. So the usual factors that a doctor will tell you are high risk for a mother giving birth are if the mother has hypertension that's been caused by the pregnancy, The mother might have diabetes that also can be caused by the pregnancy. Maybe the mother has high BMI. These are the kind of factors that doctors would usually rattle off as being high risk factors for something like a hemorrhage or a thromboembolism or needing a blood transfusion or something like that. So if you ask a doctor, you know, what are the risk factors for the mother in a pregnancy, this is what they would say. We train an interpretable model on data, and it says the three most important features in order are the size of the baby, the maternal height, how tall the mother is, and if the mother has hypertension that is caused by the pregnancy. So let me show you those two graphs. So this is the baby's estimated weight, okay? And this is log odds on the vertical scale. So this is increased risk for large babies and lower risk for small babies. So obviously what's happening is as the baby gets larger, the risk to the mother during labor goes up. And then this is maternal height, which is our best estimate of the size of the mother, which is a sort of proxy for the size of the pelvic opening, which the baby has to come out of. And you can see that the risk goes the other way here. The taller the mother, the larger the frame of the mother, the lower the risk for the mother during pregnancy. And so the model's really interesting. The interpretable model told us that, yes, the things doctors think are important, but actually the most important things for the mother's safety are in fact the simple physics of giving birth. That is, if a large baby has to come out of a smaller pelvic opening, this is going to be higher risk for the mother than a small baby coming out of a larger pelvic opening. And based on this, we created a new feature, which is like body mass index, which is a ratio of mass to height squared. We now have a ratio of baby weight to mother height squared. And it turns out that becomes the single most valuable feature we can use to predict severe maternal morbidity. Let me show you a little bit about COVID-19, and then we're going to wrap up soon. So this is data, by the way, that's available to everyone on GitHub. We're also working with some hospitals, but I can't show you the results from that collaboration yet. So this is when the patient was born. And I want you to notice two things on the graph especially. One is the vertical scale is very large compared to the other graphs we've been looking to. This is +2, +4. +2 means that their odds ratio is 5 times higher, 5 to 10 times higher. +4 means almost 50 times higher odds ratio, chance of dying. So there's a huge difference between the younger patients who are born more recently, who have like a -1, and the elderly patients who have, say, a +2 or +3. That's a difference of 4 points. So that's a huge discrepancy. Notice, just like pneumonia, there's a large flat spot where for all very young patients, risk is essentially the same. Then risk starts to go up slowly as you become older. So 1980, this would be 40-year-olds here, 50-year-olds, 60-year-olds, 70-year-olds, 80-year-olds. And we see rapid rise in risk out here at the more elderly patients, as you would expect. And there is some interesting detail, like it turns out this drop in risk is happening right at the end of World War II. And we have no idea if there's actually something interesting associated with World War II and the fact that people of this age would have traveled around the world and possibly become more protected to various immunities, that they would have collected in other places. Or maybe there's other explanations, or maybe this is just error bars, who knows? But anyway, we do see some interesting detail in the graph, and it makes us want to do more detective work to figure out what's going on. But the overall trend is, as you've seen in the papers, that being elderly does really significantly add to your risk with COVID-19. This is male-female, and here this is a pretty large difference. Scott also showed you this in one of his graphs. So here's a +0.2 for males, a -0.3 for women. And the usual explanation for this is that when it comes to illnesses, men, especially elderly men, are the weaker of the two sexes. So it's often the case that men are more likely to die, say, of respiratory illnesses than women of the same age who share the same comorbidities. Speaking of comorbidities, here's a number of comorbidities. And again, notice the scale is really large here. So chronic kidney disease adds +4 or 5 to your risk. Ignore bronchitis and Parkinson's, very few patients there. Diabetes, though, and hypertension add a lot to your risk. And then interestingly, things like asthma and COPD and having cancer and coronary heart disease, these things don't add much to your risk or might even subtract a little from your risk. And by the way, we are seeing very much the same story when we look at much larger data sets as we work in collaboration with hospitals in New York City at Ground Zero. So let me show you something else, another medical data set. There are different ways of using these EBM models. Mainly, we've been talking about global model understanding, but you can also explain the predictions that come from the model. This is more like what is often done with Lime and with Shap. And then we can even try to open up a black box model. I'll try to show you that. But let me show you how to explain predictions that come from a model. So I'm going to just give you an example of this and flip to a browser. So here's a 30-day readmission data set. The goal is to predict if you've been released from the hospital and have to go back within 30 days. Here's one patient. There are 4,000 features in this model, 4,000 graphs. This patient has an extraordinarily high probability of having to be readmitted. And we've sorted the features by how much they add to this patient's risk. And we're only going to look at like 5 or 6 features out of 4,000. So the number one feature for this patient is fat emulsions through an IV. Basically, they're getting calories added to their IV to keep them from starving to death. And this is adding 0.4 to their risk. They have what's known as cyclical vomiting syndrome. That's why they need to have calories added to their IV. And there's a scale for cyclical vomiting, and there's 16 on this scale, which is part of the high risk part of the graph. And this adds 0.38 to their risk. They're getting amitriptyline. Whoops, sorry. They're getting amitriptyline. And they're getting a pretty good dose of amitriptyline. That puts them right up here at the very high risk part of the graph. And that's adding 0.35 to their risk. Amitriptyline is an anti-nausea med. They've been in the hospital 64 times. That's an incredibly large number of times to be in the hospital. They've been in the hospital 18 times in the last 12 months. So their average readmission time is less than 30 days. And they've been in 10 times in the last 6 months. Okay, so we think we have an idea of what's going on with this patient, even though we only looked at 5 or 6 features and ignored the other 3,995 features. Here's a different patient, has only an 8 or 9% chance of being admitted to the hospital. They've been in the hospital 6 times. Ignore we often see this electrolyte imbalance. Ignore that. It actually shows up on many patients, so it's not very diagnostic here. Oh, the patient has a DX code suggesting that they have a history of things that are hazardous to their health. This is either suicidal behavior or things like driving your motorcycle at 150 miles an hour, things where you're not too worried about your own safety. They've been in the ER 6 times, so all of their hospital visits came through the ER. That's not usually a good way to enter the hospital. Oh, they have combat fatigue. So now we know this patient is probably a vet. And they have mild drug intoxication, 1 on a scale that goes from 0 to 4. And they've been an inpatient at least once in the last 3 months. So now think about this patient, very different from the previous patient. This patient is a vet. They've got some intoxication, drug or alcohol problem. Maybe they have suicidal behavior. Maybe they have PTSD. Who knows? Very, very different from the previous patient who had cyclical vomiting syndrome, who had very high probability of being admitted to the hospital. Okay, so that's that example. That just shows us that even though a model, somebody asked a question after Scott's talk, what happens when you've got thousands of terms? This shows you that that kind of model can still be very useful. And seeing the explanation in the context of the graph can be very informative when you're trying to understand a patient. Let me just wrap up by showing you this. And then my goal was to finish at 11:30, so this is perfect. So one way we can use this kind of model is to open up a black box model. So we can even try to do a little bit of what Lime and Shap are doing by training an interpretable model to mimic the black box model. So COMPASS is this model for recidivism prediction. And there's a lot of question in many papers published on whether the COMPASS model is biased, racially biased. So what we're going to do is train an interpretable model, an EBM, to mimic the black box model, because ProPublica very nicely made a data set available where we actually know the outputs of all the black box models and we know the input features. Now, this is when we train our model to mimic the COMPASS model, and also, so mimicking the COMPASS model is the red line. And green means we actually know whether these people recidivated or not. So this is actually just predicting ground truth, ignoring the compass model. And this is number of prior convictions. And as you can see, this is log odds again, risk of committing another crime goes up dramatically as your number of prior convictions goes up. And we completely agree with the compass model, that this is an important feature and learn essentially the same thing on it. But this is when we train to mimic the compass model using race as one of our features, which is certainly not a feature that's used in the compass model. Notice that for African Americans, when we mimic the compass model, we predict that they're higher risk than green, which is what we would predict looking at the real data. And for Caucasians, we predict that they're lower risk than we would predict when we look at the real data. That's a classic sign of bias. That is, we're predicting higher risk than is even warranted by the data for African Americans and lower risk than is even warranted by the data for Caucasians. So that's a classic sign of bias, and many papers have talked about this. What the papers don't talk about, though, is that Native Americans are actually the largest bias in the model, and that's because most people didn't think to look for Native American bias. Whereas when you have an interpretable model like this, it just shows you everything. You can't ignore things that are big effects. So this model, the compass model, apparently says Native Americans are very high risk, even though the data says that they're very low risk. So the model says this is not justified at all. We think the explanation for this is the compass model is trained on Native Americans around the entire US, whereas the data ProPublica had available all came from a single county in Florida, where perhaps Native Americans are much lower risk than they might be in other parts of the country. But unfortunately, this model is being used in this county. So the people who are getting most incorrect predictions for them, the most bias that impacts their lives, are in fact the Native Americans who are in this county in Florida. Okay, wrap up. Intelligibility and explanation, just critical in many domains. And we find one of the biggest uses is actually to help debug your data. But they're also important for helping like doctors trust your model. And as Scott was saying, to help you improve your model. I think Marco also talked about that. If you've got a complex black box model, or you have a complex pipeline, or both, you have to use, probably some sort of black box interpretability method like Lime, Shap, or partial dependence, or you're going to have to train our interpretable model to mimic that model so that it can sort of open up the black box a little bit. But you can only do that if you have access to the training data. So you can't use our methods if you don't have the training data. But if you're the one training the model, then you probably should use an EBM glass box model instead. There's usually little or no loss in accuracy. In fact, sometimes these are the most accurate models you can train. The explanations are exact. The models are even editable, so you can now act on the things that the problems you find in the data. And these EBMs currently are the state of the art in glass box machine learning. And as a side benefit, they're extremely compact and fast at runtime. So they're easy models to use if you want to deploy them. So if you got a choice between black box and EBM, and you can use an EBM, you probably should use it. So let me wrap up there. And then when I hand it over to Harsha, he's going to show you a demo for the last 30 minutes of the InterpretML package, which wraps up everything we've been talking about today: Lime, Shap, partial dependence, and EBMs, all into an easy-to-use package so that it's easier to compare these things side by side. But let me stop now, and I'll take questions. So how far back do I need to go here? Ooh, boy. All right. So I'm just going to start.
All right, from here on in, I'll see you with this.
Can you hear me? I'm sorry, somebody said something, but I didn't know what they said.
It might have been me, Rich.
Oh, okay.
Yeah, by the way, feel free to take 5-10 minutes and answer questions, and then we can also save some for after Sam and I are done.
Thanks. Let's see, how do you give explanations for pairwise interaction features? Is there a comparison of EBM and light GBM on accuracy and runtime? It's a great question. Typically, our accuracy on tabular data is comparable to light GBM. Sometimes we're better than it. Sometimes it's epsilon better than us, vice, but we're right up there neck and neck with them. Like GPM, we can model up to pairwise interactions. In most data sets, you'll find you don't need to go beyond pairwise interactions. In fact, it becomes exponentially harder to learn higher order interactions. So it's not a surprise, perhaps, that stopping at pairwise interactions actually for most data sets gets us there. Every now and then we do see a data set where you need something more than pairwise interactions, but not usually, and that's why our accuracy is competitive. We also don't tend to overfit the way some of these boosted packages will. Let's see. Is it straightforward to make it Bayesian? No, we are working, by the way, on ways to get better confidence intervals out of the package than what we currently do. Currently, our confidence intervals come from a bagging process. We do have a better way of generating confidence intervals, but it's not in the package yet. How to make it full Bayesian, I'm not sure, although I think it might be possible to do a form of generalized additive model using GP, using Gaussian processes, in which case then we would probably have many of the benefits of Bayesian analysis, including better error bars. Is there vertical dispersion? Yeah, no, unlike what you saw in Shapley plots, the model here is the model. So the model has learned this exact line, and there's no vertical dispersion because it is showing you what it does itself. Now, if you learned a more complex model, maybe there were important three-way interactions that our model with pairwise interactions couldn't handle. Then there should be dispersion, but our model will have just learned everything it could with main effects and pairwise interactions, and it will have ignored the three-way and higher order interactions. So you won't see the dispersion. But if you trained a more complex model, like deep boosted trees, and then did Shapley analysis, you would see dispersion. I don't know if you can see dispersion on the pairwise interactions in Shapley values, but if you could, you would see the dispersion there. The green error bars are actually plus or minus one standard deviation. And they're not kind of error bars that I completely trust because they come from bagging, and bagging is pretty good, but not perfect at coming up with error bars. If you're really a statistician, I wouldn't trust these error bars too much. We do have a new procedure for better error bars where we'll actually be able to do accurate 95% confidence intervals, but it's not released in the package yet. Retirement. This is a great question. A retirement is an unobserved variable in this data set. If we had observed retirement, then it probably would have moved. All that jump that we see at 67, 68, 69 in the age graph would have moved to the retirement variable. And we would have seen a smoother, more correct risk as a function of age intrinsically in the age graph. So I like this question because if we collected the data again, we would now know that we should add a retirement feature to it because of this bump that we saw on the age graph. And then the graphs would be even easier to understand by adding a retirement feature. Usually adding features doesn't make models easier to understand, but in this case it does with interpretable models. So this is a question about, once you're over 100, you must have some genetic factors, that make you pretty healthy. This is absolutely true. We are sure that the flatness of risk in the 90s is due to what's called selection bias for what's known as healthy agers, people who have really good genetic mix. What's telling, though, is when the risk jumps up or down at a round number, it's very hard to explain that as being some genetic factor because the genetic factor doesn't know the number of times you went around the sun, and it's not going to be a step function rise. It's going to be some gradual reduction in risk or increase in risk. So it's the step function that tells us that something's happening that's more of a social policy. I'm sure there are genetic effects that are also captured, being modeled somehow in the graph that we can't really see and prevent the risk from going even higher above, say, 90 or 95 than it otherwise would. Really good question. With correlated features, what our model tries to do, because it's a round robin model, it tries to spread. If you've got highly correlated features, it'll try to spread the signal it's learning among the highly correlated features. But if the features are only moderately correlated and you have a fair amount of data, it will try to put most of the signal on the features that best explain that part of the risk that it's trying to model. So it's a really good question. Correlation, of course, is a very, very difficult problem to solve, and we have no magic solution to it, but we are surprised at how good this model is at dealing with correlation. And we have found that this round robin kind of algorithm is really important compared to most boosting algorithms, which are not round robin at all. They'll keep going to the same feature again and again and again until they use it up enough that some other feature looks useful. It's very, very important from an explanation point of view to do something that's round robin. Okay, I think I'm going to stop there. There's another, bunch of good questions here. If you want to put them, as Scott said, on the GitHub, we will answer them that way, or you can email us. We would be happy to talk to you either during the conference or later. Thank you very much. These are great questions. I wish I could go through all of them. So. Harsha, so it's up to you now. Talk about InterpretML, the package that brings all of this together.
Right. All right. Can everyone hear me okay? I will start.
Can hear you fine.
Great. And so like Rich said, I'm Harsha. I'm an applied scientist at Microsoft, and I'm going to do this last section with Sam Jenkins, who's also here on the call. We're going to kind of trade off between the two of us. And we're going to be doing a walkthrough of InterpretML. So Sam and I, along with being data scientists at Microsoft, are co-founders and core developers on this InterpretML package. And if you want to follow along, let me start sharing my screen. Please visit the GitHub URL. So github.com/interpretml/interpret. It was pasted in the chat a few times, but in case anyone didn't see it, you should be able to grab it here. And on our GitHub page, you can find out how to install the package one and grab the sample notebooks that we're going to be talking about in this last section. So we're going to split this up into two parts, and each part's going to kind of focus on one of the major goals of Interpret. One is Interpret contains a reference implementation and kind of the most up-to-date one of the explainable boosting machine. So this is the algorithm that Rich just went into great detail about. And we're going to show you how you can practically use it and run it on your own data sets. Outside of being a reference implementation for EBMs, Interpret also contains implementations of many other algorithms. You can see some of them here. And our goal is really to expose these algorithms, make them easy to find, discover, compare, and support you in doing downstream tasks with them. So making it easy to compare these algorithms or embed them in your own workflows, your dashboards. So the way we're going to split this talk up is Sam's going to walk you through this first notebook here. Under supported techniques, you'll see a link. This is an NB viewer link. And if you want to follow along, I'd recommend downloading this. You can just save the page as a notebook and save it wherever you want and run it through standard Jupyter. And then after Sam's done, I'll take whatever time's left to show you some upcoming work that's not yet released in Interpret, but kind of a collaboration between Scott, Sam, and me on the future direction of interpretability engineering. So with that, I'm going to pass it off to Sam, and time permitting, I'll see you all at the end.
Sam, it's possible that you're muted.
Hey, Rich, do you mind checking and seeing if Sam's got, if you can unmute Sam?
Yes, I'll try to do that. I can ask him to unmute, but I can't actually unmute him myself. Let me.
All right, I think that should be good.
I answered. Hopefully you can hear me now.
We can hear you now, Sam.
Go.
Thank you.
Well, that's good to hear. All right, so I need to share the screen. So I walked in pretty late. How am I supposed to share the screen?
I think Rich needs to make you a co-host.
Fair enough.
All right, Sam, you should be good to go now.
You're a co-host now, Sam. Sam is coming
Okay.
in from Australia, so this is a very unusual time for Sam.
Oh, tell me about it. So can you guys see my screen right now?
Looks good.
All right, fantastic. All right, as mentioned earlier, apologies in advance if I pass out in the next hour or 30 minutes, whatever it is. It's unfortunately 4:30 in the morning, and I've had enough cough suppressant to make a drug user jealous, so I'll try my best to go through this. I'm going to do something much more elementary than the rest of the talks you've seen, which is walking through the Jupyter Notebook on how to use Explainable Boosting Machine amongst a few other explainers provided in interpretability. For sake of time, I'm going to go through any glassbox models. There is a black box API available as well, but yeah, you'll have to see that in your own time. So first things first, we're going to just set up a standard classification experiment, which is using the adult data set. That's when you try to predict if an individual is earning more than $50,000 a year or not. And this is derived from US Census. So it's really just what you normally do in a Python environment, do a bit of trickery with pandas and scikit-learn, get into a holdout test set or CV, whatever you need to do. And interpretability in the beginning, well, I think often you'd probably want to do a little bit of early EDA. So we expose some very basic stuff for that where you can explain the data. And in this case, it's going to give you histograms related to each individual class. Mostly because what we'd seen in practice working in the company was that for interpretability, a lot of the errors weren't necessarily coming from the model itself in terms of model representation, or was it misspecified, but more to do with the data pipeline. There usually was something, I'd argue at least 70% of the time or more, there was something a bit weird going down, which we often picked up at EDA. So that's just a standard drill. What I think you'd be more interested in right now is how to train the EBM, which Rich has spoken quite a bit on. And the way we expose it in the package is we try to make sure it's as close to a scikit API as possible. So if you're used to the passing in parameters at the constructor time, fit and predict, all that should be the same. And if it isn't, feel free to raise an issue. Sometimes we take time to answer it, but we do see it and we'll try and get to it as soon as we can. Now, what about the explanation side of things of EBM? So that's just really training and all that. Can I get things like, how is the model doing overall compared to, how do I explain a given individual instance? Well, for the overall model behavior, you call this explain_global, and that's attached to the EBM model itself. And you pass it to show, and show will just get you in this case, it'll be an inline visualization where you can look at what you see on the screen right now. In this case, it's a variable importance plot as measured by mean absolute score of the, in this case, the logits of the model. And here it's as expected. You guys can read this, I'm sure you can, and age is most critical. We can look deeper into that and see, well, how does each feature value relate to, the actual logits themselves? Well, here it is. Well, don't want to go too much into it, but when you're young, when you're less than 30, you're not earning more than $50,000 usually. Chances are you're a student, and that kind of relationship changes over time. And as you get older, surprise, surprise, you might have more promotions, you might earn more, buy yourself a Ferrari. That's on the global explanation side. On the local explanation side, looking at individual instance, it's a very similar API. Instead of explain global, it's going to be explain local, and you pass in the instances and the labels associated with it. In this case, we're going to do the first 5 test instances, and we can have a look at it. Let's have a look at, instance number 2. And this person we're going to change this header a bit, but what it's saying is, we've predicted class 1, meaning he's earning more than $50,000 a year with a probability score of 0.941. And it turns out he actually is earning more than $50,000 a year. Break it down when you look at a local explanation, and it turns out capital gain, he's earning more than $28,000 a year. Well, if you're earning that much money with investments, it's as clear as day. It's going to earn more than 50K. So it's as expected, but this is really handy for when things kind of go wrong, usually like when you have false positives, et cetera, false negatives, then you want to figure out, is there a given feature which is overfitting, or is there something which isn't operating as you'd expect, et cetera. It's more of a debugging utility than anything for these parts at least. Now that's it's good to try to explain models, but I guess like the first thing you want to check is if the model is performing well. Is it even worth explaining? Because, you know, I guess that's pretty clear. Now for that, we explain perf through ROC. You can also go through standard scikit-learn and, you know, do predict prober on the ROC scores there as well. You know, the choice is yours. In this case, we try to visualize it with a somewhat clean graph to say that, yeah, EBM is getting AUC of 0.92, and you can see the density of the residuals as well. Sometimes things kind of play up there, which is often good to see. Now, knowing that EBM has done an AUC of 0.92 on the adult data set by itself is good, but often you'll want to compare it against other models. So we're going to look at a few other ones, like we have logistic regression here, and we also have a decision tree, which we also provide an interface to through the Glassbox API. And you can have a look at it. It goes through the same API calls for ROC, explain local, explain global. Logistic regression is sitting on a cool 0.90 AUC. Decision tree is it's lagging behind a little bit. And bear in mind, this is a single decision tree, no boosting around forest or anything, 0.85. And EBM, in this case, comes out as a clear winner at 0.923. And you'll see variations with these kind of things. For Glassbox, typically EBM does best. If you're comparing against a non-Glassbox model, such as any kind of gradient boosting mechanism, it tends to be competitive. They often alternate in which one does best. Now you can look at the same thing, like explain global local again for all these models as well. And going through kind of like just scrolling up and down all the time is kind of difficult at times. So we also expose a dashboard, which you can go into more detail. So for instance, if you want to look at the global behavior of feature age of, say, what would you call it, a logistic regression relative to EBM, then you can do that. And surprise, surprise, logistic regression is going to give you a linear relationship in terms of the logits relative to the nonlinear representation EBM will learn. So there are cases where it's better to use a dashboard and sometimes there isn't. So we try to expose as much as we can there. And for sake of time, I'm going to just switch over to Harsha immediately now that this is covered. This is just like the bare bones of how to use interpret. We try to keep the API as minimal as possible. You shouldn't be learning too many things. Otherwise, you know, there's no point using it. So I'm going to pass it off to Harsha. You're on mute, Harsha.
I was on mute. Thanks, Sam. Let me start sharing my screen again. Let's see. So I'm going to do another notebook. Can everyone see my screen okay?
Yeah, looks good.
Okay. The goal here is to give you a bit of a behind the scenes peek of what's kind of upcoming in the interpretability engineering world. So please keep in mind that none of this stuff is released and is subject to change, and you're actually the first audience that we're sharing this with. So excuse us if things are a little rough around the edges. Everything you see here is a joint collaboration between Scott, who spoke 2 sessions ago, Sam and me. And we've been thinking hard about the interpretability ecosystem and how we might be able to make it a little bit better by defining more standard APIs. And I'm going to show you what some of those APIs are and how they might actually be useful for you. So I'm loading up the same Boston data set. You've seen this in Scott's talk. You saw a similar set of calls with pandas and scikit-learn from Sam just a minute ago. And I'll fit an EBM on it. And for the sake of demonstration, we'll also fit a SHAP explainer on the EBM outputs. Now, as Sam and Richard pointed out, EBMs can provide their own kind of exact explanations of how they're making decisions. But for the sake of demonstration, we wanted to have a couple different methods at play here. So one thing you'll notice right off the bat is that the signatures for how you call these things are similar, and over time you'll see that they get more and more similar. There's slightly different settings. EBMs have explanations on their own objects, and SHAP you have to pass extra objects in, but we're all actively collaborating on making these a bit easier and a bit more uniform. What I really want to focus on is the outputs of when you call these explain functions. So when you create a SHAP explainer, and call it, or when you call a function on an EBM, you'll notice that they have a same shared kind of parent object called an explanation. And I want to walk you through a little bit about what this means and how this might help you downstream. So one thing you'll notice is that these objects, we try to bundle all the useful information you might need in an explanation on one object to do any kind of downstream task you might want. So Scott and Sam have both talked about dashboards or monitoring or serialization. Having kind of a shared object means that all of these become much easier. So in this object, we've got the names of the features, the original data that we fit the local explanations on, and the feature importance values that we either learned from EBM or from SHAP. One kind of really natural operator that comes with these is wanting to slice them. So if right now I've computed these explanations on my whole test set, right? But maybe I want to look at the explanation for just the first instance in my test set. And you'll notice that you can kind of slice these very naturally. You know, it's a very Pythonic kind of operator to say, give me the first row, right? And these explanation objects will automatically slice all the relevant dimensions down to give you just what you need at the time of slicing. So you'll see that you do this for the EBM object, and you can also do this for the SHAP object the same exact way. In this case, we're using SHAP's permutation explainer, and you'll notice it's a little bit different from the EBM explanations, but configuring SHAP a bit better will have SHAP better recover the exact EBM explanations. This is just kind of a quick run for the sake of a demo. The cool thing about slicing is that you can go much further with it, right? So you can, if you want very specific things, instead of having to go through all these kind of convoluted function calls, you can just say, give me the first 5 instances, and I want the features, age, and LSTAT for those 5 instances, right? And these explanation objects are kind of smart enough to slice all the relevant dimensions down. If you really want to, you can even look at the feature names now, and you'll notice that they're only covering the 2 features that we specifically asked for. In Scott's master branch, you can see some of this already encoded, and you'll see it in interpret in the coming weeks as well. Now, what does this mean like practically, right? One of the coolest things is that you can start sharing objects across these different libraries. So you'll notice that an EBM was generated from interpret, but just as easily as generating, you know, maybe you want the waterfall style plots that you saw in Scott's library on your EBM. Well, now that these objects are kind of shared, you can pass them back and forth between them. You can pass the first EBM instance to a SHAP waterfall plot and get the same kind of breakdown as you would with a SHAP explanation. And of course, if you want to do aggregations or scatter plots, the same kind of story works. And the inverse also works as well. You can take SHAP explanations and pass them off to interpret if you want the kinds of graphs that Sam was showing you a little bit earlier. So interop is a really nice story. But one thing that we think is a little bit more interesting is building your own downstream experiences from this. So let's say that you have a very specific type of visualization or a restriction in your production environment that requires you to use a specific library, like maybe matplotlib for whatever reason doesn't work, right? In this case, we're using Plotly, and with just, you know, maybe what, 15 lines of code, you can write your own graphing code that works on any of these explanation objects, and you don't have to do all this expensive type checking or figuring out where's this object coming from and how do I access the values and the feature names, right? So with this, you can easily generate interpret style visualizations of both EBM and SHAP objects. And again, there's no conditional logic. There's no checking of where things came from. It's all just one kind of unified, harmonious experience. And as you notice, you know, as we mentioned before, there are some differences between what EBM natively produces as an explanation and SHAP's permutation explainer running in a kind of a restricted way on these EBM objects. And so, like Sam was talking about, you can do kind of top-down comparisons and see that, you know, hey, SHAP's actually doing pretty well. It's recovering most of the effects perfectly. And if we gave it a little more juice or switched out the type of explainer we were using, we might be able to perfectly recover these things, conditional on the backgrounds being the same. But, you know, if you want to do this in a more meaningful way, you might want to start building your own dashboards, right? And this is where the power of having a shared explanation object really kind of shines. With maybe what, 20 to 30 lines of code, you can easily start generating your own interactive experiences on top of these things. So here we've loaded up all the instances, and we've got a dropdown, just like Interpret's dashboard has, that lets you kind of dynamically generate these explanations. And having shared objects really makes this possible in a way that really wasn't before. In some sense, we're kind of putting ourselves out of a job, because Interpret had to do a lot of work to make this possible before, but now it's easier and shared and easy for everyone to consume. So like I said, you'll see this in Shap and Interpret and a few other libraries in the coming weeks. And we're actively soliciting feedback on this too. So if anybody has questions, feel free to raise them in the chat, or send Scott, Sam, or me an email, and we're happy to correspond with you. There's 5 minutes left, so I'll leave some time for some questions. But other than that, well, we can wrap it up here. Okay, great. Oh, and everyone, please fill out the feedback form that Amaya is linking in the chat. It would help us out a lot.
Hey, that was great, Harsha. And Sam, if Sam is still with us.
I'm really not. Just pretend I'm not here.
Thanks for showing up, Sam. We appreciate it.
No problem.
Oh, I do have one private question. If I train remotely, can I export the explainer object and then perform this visualization remotely? Explain, especially when the data sets are too large to load locally. Yes, that's one of the main kind of things that we're trying to enable with these new APIs. So you can decouple the visualization code. You know, maybe you have heavy dependencies on big libraries like Boca or Plotly, or these with where the explanations are computed. So you can serialize those explanations in kind of a unified way, whether it's coming from Shap or Interpret, send them over the wire, and then visualize them wherever you want to, right? Your server, your website, whatever. So great question. And that's the type of thing that we're really trying to enable with this new API.
Hey, Harsha, there's a question. Does the Interpret API deal with categorical features in some specific way, you know, some special kind of pre-processing, or what does it do?
A good question. We've mostly focused on the outputs, the explanation, and there is plans of encoding kind of type information in those. So you'll be able to know which features are categorical. Of course, each algorithm is going to deal with them differently. EBM handles categoricals internally. It pre-processes them in kind of an algorithm-specific implementation. Scott and Marco's packages, Shap and Lime, handle them differently. But when it comes to explanation time, we can clearly delineate which kind of features and explanations are categorical. So downstream libraries that visualize these things might know to put a bar plot instead of a line plot that connects these things. So that kind of metadata is encoded in the explanation, but each algorithm handles things differently.
Maybe it'd be useful to add 2 cents on the connection with the Shap side of things too, because I think, you know, if you've ever worked with these explanation stuffs for very long, you realize that you end up slicing things in parallel again and again and again and again repeatedly, and it's easy to misalign things. So I think that's one of the things that I find most exciting about this is the option to, you know, group mentally together a set of parallel things that are really, you know, just different, you know, channels really that we're looking at, keep them all together. So anyway, we've integrated that entirely into the Shap thing as a backward compatible API stuff that should come out soon. And so we're looking forward to seeing how these interact and, you know, hopefully create the ability for this downstream ecosystem.
Don't be shy.
Can we, one last question, can we easily compare the two, Scott's versus Rich's, within this API, or do we need to import 2 different things? The final details are still kind of being worked out around imports, but Interpret's main goal is to enable easy comparison. So you can do it especially with this new API, like, either writing your own dashboards or using some of the stuff that's pre-built in Interpret. And you'll just find that gets easier and easier as time goes by and as we integrate these more closely together. And not just Scott and Rich's algorithms, but other algorithms too. The API is kind of a shared layer that anyone can adopt and use.
Yeah, well, and I should also clarify, not necessarily that you would be comparing SHAP versus an EBM, since they sort of work at different levels. But if you're applying SHAP to like an XGBoost versus an EBM, or a neural net versus an EBM, like that's the type of transparency we want to enable.
And I think that's exactly what you'd want to do. You'd want to train a boosted tree or a neural net on some data. Use SHAP and or Lime as a way of understanding what the models learn. And then also train an EBM on the same data if you have access to the data, and see if they're very similar or what interesting differences there are. Yeah.
Yeah, and that's possible, I think, because, as Harsha pointed out, like, if you run SHAP with enough iterations on an EBM, you get the same plot that EBM spits out. And so that the differences you see are not because of some way of allocating credit, but something actually distinct in the models themselves.
And that last screen that Harsha had up, where he had two models side by side, for the most part, the SHAP and EBM attribution plots were the same, except I noticed for one of the features, it was like negative on EBM and positive on SHAP. So I don't know if that was because you had trained an XGBoost model and run SHAP on that, or if it was just not enough sample size when using SHAP to analyze the EBM.
It's the latter. It's just a restricted version of SHAP. I
thought it was a sort order change, but
maybe it was.
The specific difference, I don't think was a flip, but I think it was just a sort order. And the change there is actually the fact that we were using 100 sample backgrounds for expectations versus the full training set. That was the source of the delta.
Cool. No, that's great.
I think we're at time.
Thank you very much, everyone, for joining us. We're happy to talk with anyone who either wants to use the packages and is running into problems or issues or new features that they need. Also, if you've just got technical questions, we're happy to help you with that. In some cases, the package is ahead of the papers. So we don't necessarily have documentation in papers that can tell you everything. So sometimes talking to us is the easiest way to learn how to do something. And we're happy to help.
Yes, apologies in advance for the delays in the responses.
It could take a few years, but we're happy to help.
Hey, Amaya, is there a way for people to get in touch with us? Can we post our emails in the chat, or is there?
Yeah, I think you can. That would be good. I already posted Rich's email, but yeah, if you all want to, that would be great.
And if there are technical questions about the GitHub repos, then I thought Scott's suggestion is a really good one, which is, just post through the repo.
Yep, I've linked that in the chat.
There's already some there.
All right, perfect.
All right.
Thank you, everyone. Enjoy the rest of the conference.
Thank you so much.